All right. Well, looks like we have critical mass and we are right at 1 p.m. So it's time to start our workshop. So welcome everybody to the Introduction to Using Environmental Indicators to Inform Salmon Management workshop. It's brought to you today by the Environmental Work Group of the Coho Technical Committee and the Standing Committee on Scientific Cooperation, hosted generously by the Pacific Salmon Commission. So my name is Marisa Litz, and I'm a research scientist with the Washington Department of Fish and Wildlife. And today I will be co-hosting this workshop with the effervescent Brendan Connors. He's a research scientist with DFO. And we'd like to start today with a land acknowledgement. So I'm joining you from Olympia, Washington, on the traditional territories of the Coast Salish people, specifically the Nisqually and the Squaxin Island peoples. And Olympia and the South Puget Sound region are covered by the Treaty of Medicine Creek, signed under duress in 1854. So we acknowledge the tribal and First Nations in the US and Canada and their roles today in taking care of these lands and managing salmon populations covered by the Pacific Salmon Treaty. So a few ground rules about today's workshop. So the workshop is being recorded, and all of the talks are going to be posted to the PSC YouTube site after editing. As an attendee, the audience is going to be muted, but you have the option of posing questions using the Q&A feature or the chat box. So by now, everyone should be familiar with the Zoom platform, but these are going to be the main ways that you can communicate with the speakers or the panelists. So our chat box is going to be monitored, and we'll do our best to respond to all questions, whether we get to them or not during the time allotted, and responses will be posted on the workshop link. So respect each other and everyone's ideas, be engaged and mindful of time. We have a lot of information to cover this afternoon. There are no bad ideas or questions, and we encourage everyone to be visionary. And we're compiling a library, a reference library, and we invite all contributions on environmental indicator literature. And lastly, just the importance of the pre and the post-survey questions. These are going to be really important for guiding future workshops or seminars. And speaking of that, who are our participants today? So of the registrants, we have approximately a 50-50 split between Canada and the US, and some I expect they're from the Secretariat representing both the US and Canada. 30% of the respondents identified as serving in executive, management, or policy roles, with 70% who identified as serving in science roles. Now, the objective of today's workshop, we want to share background information, perspectives, and examples of the use of environmental indicators to inform salmon management, using both Western and indigenous knowledge. And this workshop is intentionally introductory, and it's envisioned as the first of a series of workshops addressing requirements of the new PST Annex to be responsive to changes in productivity associated with environmental conditions. And given that we're going to be dawning on a new renegotiation of the chapters in a few short years, we really want to begin to be responsive to this as soon as possible. So we have a fairly packed agenda. We have it broken into 3 sections with 2 short breaks. The first series of talks are introductory information and background information. After that short 10-minute break, we're going to switch into more of an applied section of talks using environmental indicators to inform management. And then lastly, we have a half an hour for a panel and group discussion with all of the speakers. So a little bit more about the attendees. 40% of respondents said that they rarely or never use indicators in their PSC role. And 60% said they sometimes or always did. And of those, 35% of the respondents said that they used indicators to quantitatively inform the pre-season forecasts. And of the folks that said that they didn't use environmental indicators, 20% said it was because of conflicting information, and another 20% reported not using indicators because of inadequate information regarding risk and uncertainty. So the goal of today is to alleviate some of that concern, making folks more comfortable with the use of environmental indicators. And with that, here's the high level 30,000 foot assessment of what an environmental indicator is. So an environmental indicator is a quantitative measure that helps provide insight into the state of the environment. It can be measured over a broad range of spatial scales, from basin-wide to very local. Environmental indicators respond predictably to ecosystem change and are relevant to management concerns, such as salmon survival and distribution. And to be useful for decision-making, indicators must be available in a timely manner. So in no sense, a really useful indicator that's only available up to a 5-year lag period is not helpful. Lastly, indicators can be shared with both the public and policymakers to help make informed decisions. And these can be pre-season or in-season. And with that, I would like to turn it over to my co-host, Dr. Brendan Connors, for a few words about the Standing Committee on Scientific Cooperation.
Thanks, Marisa, especially for the reference to my effervescence. I've been called lots of things in my life, but I don't think that's been one of them, so that's a first. Yeah, good afternoon, everyone. Thanks so much for joining us. As Marisa mentioned, my name is Brendan Connors. I'm a research scientist at Fisheries and Oceans Canada. I'm a pretty new addition to the PSC family, having taken over Carmel Lowe's role as the Canadian co-chair for the Committee for Scientific Cooperation a couple months ago. You may ask, what is the CSC? Well, the CSC's mandate is to help the Commission advance its scientific agenda by identifying emerging issues that require new or additional research, and by presenting scientific information back to the Commission. And of relevance to this workshop, the committee has recently been tasked by the Commission to undertake an inventory of the assessment models and management frameworks that are used by the PSC writ large, to identify if and how they incorporate environmental information, and if and how they're responsive to environmental change. And so the committee is tackling this by chapter. We're undertaking this inventory and drafting an inventory by chapter that will ultimately be shared back to relevant panels and technical committees. In fact, I think we have almost 3 inventories that are just about ready to be shared shortly, with the remainder coming over the next year or so. The idea is that we will then use these inventories and the information that's compiled to analyze best practices, barriers, gaps, and opportunities, so as to be able to ultimately develop some recommendations back to the Commission on how it can adapt approaches, management approaches, and assessment approaches to environmental change. So that's just a bit of a snapshot of where the Committee for Scientific Cooperation is coming from and the task at hand. So before we transition to the main event, what everyone's here for, just wanted to remind you, as Marisa's already mentioned, there'll be a post-workshop survey that'll come out in the next couple of days. And it's going to provide you with an opportunity to provide us some feedback on the workshop, what you liked and didn't like, as well as ideas for future events, whether they're workshops or seminars or other flavors of things like that. It's also going to provide all of you with an opportunity to provide us with more general input and advice on current barriers and opportunities to making the PSC more responsive to environmental change, as well as suggestions for how it should adapt to the increasingly variable and uncertain world in which the PSC needs to operate. So we really value your feedback. Please, if you have the chance, take a few moments to share your input with us later this week. So with that, thanks very much. Marisa, if you can stop sharing your slides, and Gary, if you're able to pull yours up, we'll move on to the presentations. While Gary's doing that, I'll just make a couple introductory remarks. Looks great on my screen, by the way, Gary. So it's my absolute pleasure to introduce someone that probably doesn't really need much of an introduction to the PSC family. Dr. Gary Morishima of the Quinault Nation. Gary's had well over 4 decades of experience in natural resource and fisheries management, and has been involved with the PST since its inception, including having served on numerous special expert panels established by the Pacific Salmon Commission and chairing a number of technical committees. So many of you have interacted with them probably in different ways, shapes, and forms. An interesting bit of trivia and tidbit of information. Back when the US and Canada finally reached agreement on the Salmon Treaty in 1985, after over a decade of pretty hairy negotiations at times, the chief US negotiator asked for recommendations on a name for the new treaty. Gary pushed for the Pacific Salmon Treaty, which we now have, because of the acronym PST, which he explained was short for the PSSST, or the Pacific Salmon Super Secret Talks, which from his perspective really reflected the nature of the discussions amongst various groups that have been going on for years leading up to the treaty, and which often left participants really pissed. So that's a bit of a arcane PSD trivia, if you will, and I'll turn things over to you, Gary, to talk about environmental change and the Pacific Salmon Treaty.
Well, thank you, Brendan. I'm going to share just a few thoughts to try to get some stuff to ponder as we embark upon our journey today. One of the things that I wanted to deal with is that not so long ago, salmon were so abundant that they could sustain whole communities, cultures, and economies. But it didn't take long for overfishing and development to take their toll. In the early 1900s, we had the Hell's Gate Slide. In 1930, there was the Fraser-Sockeye Commission. In 1937, the predecessor to the PSC was established in the International Pacific Salmon Fisheries Commission. In 1957, Fraser Pink were added. And in the mid-1970s, the exclusive economic zones were established offshore, which really set the stage for coastwide cooperation in terms of conservation of species like Coho and Chinook salmon. That led to the negotiation of the Pacific Salmon Treaty. Article 3 of the Pacific Salmon Treaty contains a number of principles that require extensive cooperation in research, management, and enhancement between the two countries. And one of those was to account for annual variation. So when the commission was established, it was a formidable challenge, even with the abundance that was available at that time. And Hubris really told us that we could do this, but salmon have not really fared well. We are looking at increasing incidence of salmon being listed under the Endangered Species Act in the United States and the Species at Risk Act in Canada. And even in Alaska, we're seeing signs of concerns for Chinook salmon. So what we're doing now, it clearly isn't sustainable. And we've got to think about what we're doing today in terms of what it means for tomorrow. We're talking about environmental change and climate change on salmon in the Pacific Northwest, and that's really kind of a hot topic. The new normal, marine heat waves perhaps, the blobs are becoming more and more important, but really is there any such a thing as the new normal? Unimaginable things are happening. We're seeing unprecedented acceleration of concentrations of carbon dioxide, and even some of our river systems are beginning to shift. We're seeing ecological changes in terms of algal blooms and dead zones. We're seeing chemical relationships being developed and biological and disease pathogen vectors appearing. We're seeing food webs change with predation by marine mammals and birds. And we're seeing global warming and other things are changing as well. For example, all the dams that have been built on the Columbia River, or fishing activity that has affected the ability to sustain some of the populations that used to sustain many cultures and economies. But not only are the numbers getting smaller, fish are getting smaller too. And that holds implications for things like maturation schedules, productivity of the salmon populations. For coping with environmental change, physical ocean and atmospheric currents are involved, environmental indicators. We're going to hear about some of those today. The marine birds, some biological indicators as being potential ways of helping us identify some potential factors that are influencing change. And we're going to hear a little bit about traditional knowledge as indicators of salmon abundance. Salmon, water, environments, and habitats are all changing pretty quickly. And the world is changing too. And the challenge of sustaining and restoring salmon in the face of environmental change is going to be difficult. There are lots of factors that are involved. We need to figure out what's broken and what we can do to fix them. And one of the challenges we deal with is sort of like Humpty Dumpty, where once Humpty Dumpty is broken, can all the king's horses and all the king's men put the broken cycle of life together again? Will it ever be the same? The environment is changing, but are we? We are using aging tools and methods. Will they serve us in an increasingly uncertain future? And what does the future hold? With global change, we've got climate models and local environmental impacts that are difficult to assess, but one thing is certain, there's a lot of uncertainty in the future. And we can't forget about abrupt change or the potential for climate tipping points to bring about rapid and large environmental change and very little notice. Also coming our way is a real tidal wave of new information and observations. Here's a graph just showing the number of climate-related publications over time. And you can see that it's really hard to try to keep up on what's going on and figure out what's good or bad. And there's a danger that we could get caught up in paralysis by analysis. Uncertainty is what's certain. We can ignore it, we can try to study it, or we can try to own it through concepts like resiliency and robustness. Pacific salmon are rather unique and important in facing our environmental challenges. They're sustained by repeating cycles of life, being anadromous, semiparous, with a high degree of homing fidelity. That means there's going to be unique stresses from many ecological, social, economic, and political forces. When you add environmental change to this, it means that we are going to have to be nimble and adapt, figure out how we're going to maintain diversity, look at precautionary management approaches, and develop actionable options that can be communicated in terms of likelihoods and outcomes of risks. The road ahead is going to be bumpy and twisty, and where there's no path, we've got a blade zone. To sustain salmon and environmental change, we're going to have to face some very difficult challenges, many of them being wicked, being independent, multi-causal, very socially complex, and involve changing people's behavior. We're going to have to look beyond our nose to extend our vision, to stop and think to the past, to the present, and to the future. And remember that we're dealing with interdependencies, that salmon are ecological and institutional integrators. They're ecological integrators of land, water, oceans, and their creatures, and integrators of fragmented institutions of agency and political governance. The need is urgent. We're running out of time, and we don't have the luxury of waiting until we know it all. The stakes are high. The future of salmon and the salmon people are at great risk. But remember, it's not just about fish. Salmon are like our miner's canary of what's happening to our environment. And if we can find the will and the means to sustain abundant, productive salmon stocks, then maybe there'll be hope for us as well. Lastly, I'd like to share with you a little message from one of my favorite characters from Star Wars. May the Force be with you. Thank you.
Well, thank you very much, Gary, for kicking things off and the strong call to action. Really appreciate you sharing those thoughts and those slides with us. I'm going to be turning things over to you, Laurie, here in a moment. I did want to just take an opportunity to let everyone know and remind everyone, attendees in particular, that you can pose questions for all the subsequent talks, not Gary's, but everyone's after that, by putting questions into the Q&A box. If you scroll down to the bottom of your Zoom console, you'll see a Q&A tab. So feel free to put those in as the talk's going on or right as the talk ends, and you can vote them up and down, and I'll be reading those off, or Marisa later on will be reading those off to our presenters. So Laurie, if you're able to pull up your presentation, please.
Can you see that?
It's here now. Thank you. So next up, thrilled to introduce Laurie Weitkamp from the Northwest Fisheries Science Center, where she's been since the early 1990s. Laurie's research focuses on the ecology of salmon in estuarine and marine environments and the influence of physical and biological processes on salmon survival and their distribution at sea, which is what she's going to be talking about today. Laurie's left-handed and comes from a long line of left-handers. In fact, her paternal grandmother was left-handed, and about a third of all of her descendants are left-handed too. And so Laurie tells me that as a result, the left-handed contingent of her extended family always sits on the same side of the table when they get together at family gatherings to avoid bumping elbows and spilling drinks with the right-handers. As the title says here, Laurie's going to talk to us today about how Pacific salmon are distributed at sea. And so with that, please take it away.
Thank you, Brendan. I'm going to be talking about where salmon go in the ocean, because I think it is an important first step to select environmental indicators you're interested in. It's really important to know where they are during critical periods when the mortality is high and there's strong influence from environmental drivers. For example, you probably wouldn't use air temperature in Paris, France to help you predict chum salmon from the Yukon River. So you need to know where these fish are. It's also important to know where they are throughout the ocean phase in case you want to look at indicators later in life after these critical periods, because salmon are moving around in the ocean. They very rarely stay still for any length of time. And it's also important to realize that different species and stocks use the ocean differently. So what indicators that work for one species may not work particularly well for another. And in thinking about indicators and where salmon are in the ocean, I have 3 phases of ocean residence that I personally think are important. The first is the critical spring and summer period. Their first spring and summer in the ocean. At this stage, the fish are quite small. The mortality is high and highly variable. And the factors affecting survival are the abundance of high quality prey that fuel rapid growth to outgrow predators. And both the prey and the predators are strongly impacted by environmental conditions. So we believe most of the mortality occurs during this first spring and summer. It's a critical period. And this is when most indicators are people are focused on this early ocean period. But salmon spend a lot longer than that out in the ocean. So during subsequent winters and summers, the mortality is lower and less variable. We don't have a good idea of the factors affecting survival during later stages of ocean residency, other than we think that growth in the summer is important to avoid winter starvation. And this first winter in the ocean has been identified as a second critical period for Pacific salmon. And then finally, there's the last spring and summer. At this stage, the salmon are quite large, too large for most predators. Mortality is low, more or less constant, but they do need prey for final growth and gonad development. And the reason I put these 3 phases on is that most of the time that salmon spend in the ocean, which can be in extreme case, 5, 6, 7 years, is in the subsequent summers and winters. And I broke off the last spring or summer in the ocean just because we have a good sense of where individual stocks of salmon are at that time. So what I'd like to do is show you a series of maps maps showing different phases of ocean residency. At the top, I'll have the species name. This is the order that I will be showing them. So both coho and pink salmon just spend 1 winter in the ocean. So that affects how far away they can go from their natal streams. And then chum, sockeye, and Chinook salmon spend more than one winter in the ocean. And these are very broad brush descriptions. There's a lot of variation both within and among populations, and it's kind of beyond the scope of this talk to be able to get into any kind of detail. I'm going to be showing you this map. This is North America with the Gulf of Alaska, Bering Sea, and then this white strip along the North American coastline is the continental shelf, which is somewhere between 20 to 80 kilometers wide, depending on where you are. And this continental shelf is incredibly important for juvenile salmon during their first summer and fall in marine waters. In subsequent winters and summers, we actually don't know very much about where particular stocks, let alone species, really are out in the ocean, particularly the winter period, although recent research has helped inform some of that. And then during the last summer, there's still a lot of variability in our knowledge of where these fish are, mainly for fish that are moving from offshore areas quickly onto the continental shelf before they go upstream to home. So they're really not intercepted by very many fisheries, so we don't understand where they are. And the data sources I'll be using, there's a new book out, 2018, called The Ocean Ecology of Pacific Salmon and Trout, that has great descriptions of the movements of salmon across the entire North Pacific. And then this wonderful paper by Kate Myers, which summarizes 50 years of tagging data. Before I get started, I think it's important to recognize that steelhead are really different than the other salmon I'm going to be showing you. So this is from Kate Myers' chapter in the book that Dick Beamish was an editor, and it just shows that the top graph is juvenile locations during their first summer in the ocean, and they move straight offshore. When they come out, they don't spend any appreciable time on the continental shelf. And then the subsequent summer and winter distributions of both summer steelhead and winter steelhead stretch across the entire North Pacific. So they're all the way over, almost to Japan in the case of summer steelhead, a little bit less widespread and further south in the winter. And then when they return to the freshwater, they just go straight in. They're not spending any appreciable time on the coast. And so indicators that people have selected for steelhead don't work very well for other species, or more likely, the indicators that people have for other salmon do not work for steelhead because their patterns are so different. Okay, so here is Coho salmon. Again, this is just one winter in the ocean. And during their first summer and fall, we actually think they have two general behaviors. One is active migration, where they're moving north and west along the shelf, and this is indicated by the brown arrows. And then the other behavior is to remain in local waters. So they're really not going very far. They come out onto the shelf and then more or less hang out there. And that includes populations that are in Strait of Georgia and Puget Sound. During the winter, we think they're offshore in the Gulf of Alaska. As I mentioned, recent surveys out in that area have picked them up, but there's also populations that remain within the Strait of Georgia and Puget Sound. And then during their last summer and fall, they move from offshore areas onto the continental shelf, perhaps a month or two before they move upstream. And so they're caught by quite a few fisheries as they're moving in, not as extensively as Chinook salmon, perhaps more extensive than other salmon like chum, sockeye, or pink salmon. So for pink salmon that are also spending one winter in the ocean, during their first summer and fall, they come out and slowly move north and west as they're remaining on the continental shelf. For Western Alaska populations of pink salmon, they're in the Bering Sea, where they appear to be kind of milling around. And how far north they are in the Bering Sea really depends on the sea ice extent. And I just put the timing down for Fraser pinks. They leave the Strait of Georgia sometime in the summer, perhaps early fall, depending on the population in question. They're up in northern British Columbia by late summer and moving offshore into the fall. During the winter, we know they're out in the Gulf of Alaska. They appear to be somewhat further south than other species in the Gulf. And then during the last summer, we know that they move from offshore, onshore to the continental shelf relatively quickly in that they don't spend a lot of time on the continental shelf before they're moving upstream. Just they're not susceptible to extensive fisheries. They exist on the continental shelf. So chum salmon, now we're moving into species that spend more than one winter in the ocean. They have a fairly similar pattern to pink salmon during their first summer and fall, in that they move out onto the continental shelf and then follow it around up to Alaska, perhaps out in the Aleutians. Western Alaska populations of chum salmon remain in the Bering Sea before they all move offshore. For Fraser River chum salmon, they have extended estuarine residence in the Fraser estuary. They're leaving the Strait of Georgia late summer, early fall, up in British Columbia sometime during late summer, early fall, and then offshore in the later fall. And they're really interesting in that their distribution in the winter is in the Gulf of Alaska, and in the summer they move up into the Bering Sea. But it's not just North American populations that are doing this. It also includes chum salmon from Japan and Russia. And in fact, some recent winter work showed that the Japanese chum salmon actually outnumbered North American chum salmon in some parts of the Bering Sea. And then during the last summer and fall, they're moving from offshore onshore and don't spend a lot of time on the continental shelf before they head upstream, because they're not subjected or not caught by a lot of the fisheries that occur on the shelf. Sockeye salmon have a fairly similar pattern to chum salmon. So they're on the shelf, moving up to Alaska. Fraser sockeye salmon, there's a lot of variation between the different populations. We think they're leaving Strait of Georgia sometime in June. They're up in Southeast Alaska by summer and move offshore in the shelf, or offshore in the fall. And particularly Bristol Bay sockeye are making extensive use of the Bering Sea during their first summer and fall in marine waters. Their subsequent winter and summer distributions look fairly similar to what we saw with chum salmon, where they're moving between the Gulf of Alaska and the northern Gulf of Alaska and Bering Sea in summer. Except for sockeye, their North American sockeye distribution extends quite a ways west, further than perhaps any of the other salmon I'm talking about here. And then as far as their last summer and fall, it appears that they're moving relatively rapidly from offshore areas onto the continental shelf and upstream based on their limited catch by coastal fisheries. For Chinook salmon, I've split the Columbia River spring Chinook out from other populations just because they're fairly unique in that they come out of the Columbia and they just zip north, moving incredibly rapidly. They're up in Southeast Alaska by June, after a month after entering marine waters. We're not really sure how far out they go before at some point we think they head into the Gulf of Alaska for their first winter in the ocean. And then in subsequent winters and summers, we know they're moving between the Bering Sea because they're caught as bycatch in the pollock fishery. But where they go during the summer, we're really not sure. And they have been recovered by fisheries as far south as California during summer, but they are few and far between, very few numeric compared to other salmon species. And then during the last spring, we think they more or less go straight in to the Columbia without spending much time, largely because they're not caught by fisheries, but there aren't very many fisheries in that time of year as well. For other Chinook salmon, they really show a unique pattern in that they appear to be locally resident along the continental shelf or the Bering Sea. They're not really moving quickly. And we also have groups that are hanging out in Southeast Alaska, as well as Puget Sound and the Strait of Georgia. So they're kind of milling about, eating and not doing any kind of directed movement per se. During the winters and summers, similar pattern, except in this case, we think there are a lot of the fish that are up on the shelf. So some out in the Gulf of Alaska in winter, but also a lot that are actually on the continental shelf. In summer, then they extend their range up into the Bering Sea as well, where they, like I said, get picked up in pollock fisheries. And then as they return, they do come onto the continental shelf and spend quite a bit of time there. For example, the Chinook salmon that are originating from the Fraser River, Puget Sound, even the Columbia, are caught by fisheries from kind of central Alaska, certainly southeast Alaska, all the way down to their home stream because of this extended residence time on the continental shelf. So just to summarize what I've told you, there really seem to be two patterns for the first summer. One is this rapidish movement along the continental shelf as they're moving north and west. This is by most species. And then this resident pattern along the shelf or in the Bering Sea. This is true for most Western Alaska salmon species, as well as Chinook and Coho that are along our shelf on North America. The subsequent winters and summers, they're moving between the Gulf and the Bering Sea. And then the two patterns we see as they're returning home. One is that they move from offshore, don't spend a lot of time on the continental shelf before they're moving upstream, versus those that do spend a lot of time on the continental shelf. And I should just end by saying that there's a lot of new stock-specific location information that is being published in the last couple of years, and I expect to see more that is based on stock identification. And if you want more information, please see me and I can provide some readings. And with that, I will open it up for questions.
Great. Thanks, Laurie. Really appreciate that. Reminder for everyone, you can enter questions in the Q&A box. And we do have a question here from Will Atlas. I don't know if you can see it, Laurie, but I'll just read it out for everyone. Laurie, do we think that Fraser Spring Chinook have a similar at-sea distribution to Columbia springers?
You know, I looked that up and I was not able to find a lot on it. That one of the issues is that there aren't very many of them, and it's a really big ocean out there. And I will look that up and just try and find more information. But I did not. The Columbia Spring Chinook really appeared to be pretty distinct compared to others. You would think that the Fraser River would also have a similar pattern, but I was not able to find a lot of information on it.
Thanks, Laurie. While we're waiting for other questions, I had one quick question for you, Laurie. I'm curious, to what extent do we know about how variable the general patterns that you described are from year to year within species? And, you know, I recognize there's a paucity of data, but, you know, what do we know about how much interannual variation there is, and what types of processes or environmental conditions might be correlated with that? And what does the future hold for these kind of the predictability of the types of patterns that you've described?
That's a really good question. Generally, we think they are really stable in time, even though there may be poor environmental conditions. They're swimming through areas that don't have a lot of prey. They still follow the same ancestral feeding routes. And I say this is based entirely on Chinook salmon. So I've done some analyses looking at adults, and Strom Tucker with DFO looked at juveniles, interannual variation in the pattern, and did not see really strong variation. And that's one of the concerns, is that these are these ancestral feeding routes that have been successful over thousands or tens of thousands of years. And so how are they going to be able to adapt to something that requires a very different pattern? We know there's diversity within that. Not all of them do the exact same thing, but it is tough to really change what is a genetic pattern, essentially.
Thanks, Laurie. I've got another question here from Jeremy Jordan. If you had to prioritize which species need most additional work vis-a-vis ocean distribution, what would you recommend?
I think it really depends on what species you're interested in, because they all, you know, I think they're all facing this ocean that in some ways doesn't look, certainly with these heat waves we've been having, it looks really different. They're finding different prey, temperatures are different, et cetera. And I think all of them need further investigation, particularly this high seas phase where we really, the details are completely unknown.
Great, thanks. I've got a couple of questions coming in from panelists which can't use the Q&A. So I see the most recent one here from Nate. Laurie, do you think the assumption that mortality rates in those second to later ocean phases are really stable? Like, I think you had a generalization there on your, you know, I wonder if you can dig into the evidence that supports that statement.
The evidence that supports that statement is that jack rates, the percent of the number of jacks returning, is often a really good indicator of how many adults will return in the following year. And I think that in many cases, or increasingly, is falling apart, because I think actually that subsequent winters and summers, there's getting to be more mortality due to things like heat waves. And so, that I think the schedule of mortality may be changing, particularly when you get these extreme conditions. But the jack to adult return is what kind of the bread and butter that most people use to forecast returns.
Okay, thanks, Laurie. We're gonna stop the Q&A at this point, and we're gonna move on to Chris. But I just want to remind everyone that any comments, questions you put in here that don't get addressed, we're gonna make sure we compile these and do our best to have folks respond to those post workshop. So next up, my pleasure to introduce Dr. Chris Harvey. Chris, well, I'm just giving the introduction. If you're one step ahead of me, perfect. Chris is also from the Northwest Fisheries Science Center, where he's been for the past 20 years. Chris's research focuses on the ecology of aquatic and marine food webs and how their dynamics are influenced by things like fisheries and climate variability and change. Chris is the co-lead of NOAA's California Current Integrated Ecosystem Assessment Team, which synthesizes information, ecological, economic, and social information to inform ecosystem-based management along the US West Coast. And he's going to be talking about that here today with us. But a fun fact about Chris, before I hand it over to him, is that he was a roller derby referee for 6 years, which I'm told requires excellent ability to skate backwards, sideways, and practically inside out, as well as looking sharp in a zebra striped wardrobe. So with that, Chris, I'll hand things over to you.
Thanks a lot. Yeah, it was something like that. I'm also left-handed, so 2 in a row. I'm speaking to you today from Tacoma in the traditional lands of the Puyallup tribe of Indians, and it's an honor to be with you. So I'm going to talk through some of the environmental indicators that we use in the California Current Integrated Ecosystem Assessment, or CCIEA. I'll probably barf that acronym out a lot, and I apologize in advance for that. Just to anchor us a little bit here, I'll give you some background, then walk through some indicator examples that we use in our reporting each year. We'll look a little bit at our online indicator data and some of the tools we have there, and I'll talk a little bit about some applications of indicators as well that hopefully will be helpful context. So just to start with some background on the IEA process, the Integrated Ecosystem Assessment process and indicator selection. What the CCIEA team does is to compile indicators, dozens of them, in fact, each year into annual ecosystem status reports. And the main customers that we have been serving for the last 10 years or so that we've been doing this have been the Pacific Fishery Management Council and the NMFS West Coast region. And they generally are looking for general context from the products we provide them. The indicator, or the diagram here on the right, is to remind you that indicators aren't exclusively things like how warm it is in the water, how strong upwelling is, how much nutrients are out there. It also includes things having to do with the human domain of the ecosystem, human activities, human objectives like improved well-being, and external drivers in the human system, like local and more large-scale social systems. Just want to make sure that that point is kept in mind. We maintain an online indicator data portal as well, and I'll talk about that a little bit. And as I just mentioned, our suite of indicators includes climate, oceanographic, ecological, economic, and social indicators. And we've contextualized some of these for salmon, and I'll try to talk about that a little bit too. For time constraints, I won't really talk about the economic and social side as much as I would like, but there we are. The IEA framework looks like this. You probably see lots of framework diagrams in presentations and papers anymore. So I distilled it into this, and this is the rubric that we try to follow in our work, which is to just, with our partners, we ask what our goal is for an ecosystem, what the status of an ecosystem is now, what pressures, risks, and unknowns are between us and our goals for the ecosystem, and then what do we do about it with management. And then we constantly are revisiting and updating and repeating this process. For this to work, indicators are really important just about every step of the way in terms of coming up with what you want to achieve, how you would measure if you're achieving it or not, and then just getting a sense of how much different supportive elements and threats are out there in the system. And that's where indicators really come in. We look at lots of indicators of physical conditions along the West Coast and in the North Pacific. Some of those include large-scale climate and ocean conditions, regional ocean conditions, and then we move into because of salmon, we move into the inland streamflow and snowpack as well. And just to give you a quick flavor of what those are like and how we present them, I'll start with the telescope zoomed way out. We collect lots of basin scale climate and ocean indicators that we generally express in time series like these ones over here. And those help us to track large scale variability in ocean conditions throughout the North Pacific on time spans that would range from seasonal change to annual or even decadal change in conditions. And these, I hope, are familiar to a lot of you. Things like the index of whether we're experiencing El Nino or La Nina conditions, whether the Pacific decadal oscillation indicating the sea surface temperatures is relatively warm or cold, depending on where you are. And the North Pacific gyre oscillation is another one that we focus on that indicates how much trans-Pacific water is flowing down into the California current or turning left and going up into Alaska. I also blocked out the last 5 years of these time series just to let you know that we try to focus on at least some of our reporting on what's most recently happening so that our customers can see if conditions are relatively above or below average, if they're trending down, or if, let's say they're stuck way below average, indicated by that little minus sign there. We don't just look at things in terms of time series, we also look at things in terms of space. Again, staying at the basin scale, these are some maps of sea surface temperatures that are derived from satellites, and we pick up a lot of other information from satellites that allow us to do things like ask where different hot and cool spots are in the ocean, related to what Laurie was just talking about. Depending on where and when conditions are relatively warm or cool, that could affect different stocks of salmon. We can also ask if the year as a whole is warmer or colder than average, and if trends are heading in one particular direction. And these spatial types of information have really been helpful with all of the marine heat waves like the blob that we have been having lately. Allowing us to look at where the deviations from average temperatures are the strongest, outlined and in red here, and watching how those changes in average conditions to, let's say, above average temperatures during a heat wave are evolving over the course of a year and moving around the ocean. This is the one that occurred last year, which was the second largest marine heat wave on record for the North Pacific. And we, of course, want to consider what's happening below the surface of the water, too. So we use lots of shipboard data along the West Coast to look at subsurface conditions, such as temperature at different depths, and express that in terms of whether something is above or below average temperatures. So above being the warmer colors and below average being the cooler colors. And this helps us get a sense for how deeply into the water column some of those climate events are penetrating. So like over here, you can see an El Nino event can penetrate quite deeply into the water column along the West Coast. This is the major El Nino event of 1997. Whereas the warm blob, the big heat wave from a few years ago, was more surface oriented in much of the Pacific. So this is definitely helpful in giving us a sense of the different ways that the different climate events express themselves. We also use not just data for collected in the field or by satellites, but also a lot of models are coming into play for our indicator reporting. Circulation models are being used right now to generate daily estimates of upwelling at different points along the coast. both of upwelled water in this plot, and we can also look at upwelled nutrients. But this gives us a sense of, say, this is information from 2020, and you can see that the model predicted some large spikes in upwelling followed by relaxation periods relative to what the average variability is. So that's indicative of good conditions where you're getting injections of nutrients followed by relaxation periods that allow the system to take those nutrients up. So that's pretty useful information. The same models that generate this circulation information and tell us about upwelling can also be used to look at how squeezed up against the coast that upwelled water is. This is work that Jared Santora has led on habitat compression, and you can see a couple of contrasting examples here from 2016 where basically all the water along this part of Central California was relatively warm until upwelling began, and you can see that cooler water started to show up near the coast. And you can track that kind of index through time as well and see that, say, over the last 5 or so years since the blob occurred, that amount of cool water has actually been expanding during the wintertime in this same area of the coast. So both the spatial exploration of data as well as the time series is valuable. And then finally, same idea, we include maps as well as time series of things like snowpack broken into different regions, watersheds or ecoregions of the West Coast that feed into the California current. And then we've been scaling streamflow data, not just to these large basin scales, but also looking at streamflow compared or that's specific to particular salmon evolutionarily significant units, ESUs. And what this helps us do is look at just summarize a whole bunch of different ESUs, as you can see in this list here, and look at how their flows, the flows that they experience are changing. In this case, the maximum flows that different ESUs are experiencing are kind of all over the place. But if you look at this summary plot, the minimum flows for a lot of our ESUs are really concentrated down here in this quadrant of the plot, which means that they are, relatively speaking, they're below average compared to the long-term data, but they're increasing slightly. No, I'm going rather fast here. I apologize for that. Some ecological conditions and responses that we also want to consider, just to translate how those physical drivers are manifesting themselves in a system. We do that by counting things, by trying to get a sense of indicators of their feeding conditions, also looking at things like distributions and diets. Like I said, shipboard surveys go out and count different species that are out there, such as sub-yearling Chinook and Coho salmon that our colleague Brian Burke, who's on the call, leads this work with a lot of other people. So it's good to know how many things are out there of different species, but we also care about the conditions that they encounter once they get out there. So we look at feeding conditions expressed by things like high quality lipid-rich zooplankton like copepods from northern waters compared to copepods from more southerly waters, and this happens off of Newport, Oregon. And we're also looking at densities of other kinds of food like krill, which we're able to express in heat maps. And you can see, for example, this is a really good example of an effective indicator where krill were quite abundant off of Oregon in 2013 and 14. After the marine heat wave moved into the area, krill numbers dropped off steeply by several orders of magnitude. I'm going to skip past this because it's a little complicated. I just want to note that we also look at other things than just the amount of food available to the species that we might be interested in. Like, we're not just looking at salmon food because we can't be everywhere at once sampling all of the different prey communities out there. So we also look at what other predators are eating and let them do the sampling for us. So, and that translates into successful numbers of young being raised by seabirds. Seabirds are really effective sentinel indicators. So here we're looking at the number of young produced by seabirds on the Farallon Islands off of California. And you can see patterns in how some years they produce very few chicks and other years they produce quite a bit, which we would translate into a sense of there being good food availability for them in years where lots of chicks are produced. I'm going to hop away from the presentation and just give you a taste of our indicator portfolio that's on our website. It's our web address is a mouthful. I'll make sure that it's available to you, or you can just Google California Current Integrated Ecosystem Assessment. But we maintain an online data portal that brings in indicators from lots of different sources. And under the indicators tab here, there are many different components or attributes of indicators that we have. So if you just were to go to salmon and just select one of these are escapements of Chinook salmon to different sites along the West Coast. So if we were to look at, let's say, one of these ones that's a little bit more up to date, this is data from the Willamette River. Spring Chinook returns, and here's the same trend that you saw before, along with information of where the indicators came from and some information about how they were tabulated. You can also download the data and get some more information through these links. And we have indicator data like this for different species, for all the physical drivers that I talked about a second ago, like say, El Nino and PDO and things like that. So these are just the way that we present data in just simple tabular form. What we need to do is evolve away from these static forms of data presentation in those annual reports I talked about, and hopefully provide data that are available and updated more in real time and are tailored to the customers that need them. An example of how we're doing that is on this project page on our site that's dedicated to the topic of whale entanglement. And for the regional office and other groups that are interested in whale entanglement, we're starting to develop this data dashboard that's a little bit more interactive. So here is one indicator. This is the indicator of habitat compression. That's that water being squeezed against the coast that I talked about before. And here we've got it tailored somewhat so that you can scroll out to expand the amount of time that you're looking at or bring it in. If you're in this red zone down here, it's indicative of warm water really squeezed up against the coast, high habitat compression up here in the green area, lower habitat compression, more cool water, which is better habitat for the whales in their prey, and it keeps the whales out in deeper water, potentially away from where the fishing gear is. And other elements of the site allow you to toggle different indicators on and off. And these little icons, if you hover over them and click, you'll get a little bit of information about what was going on in a particular year. So we're working toward making our website be more of the destination for where people go to for information on our indicators. Back to the presentation, what do we do with all these indicators? How do we apply these in management or at least getting a sense of what's going on out there? A lot of it goes to what Laurie was talking about knowing where salmon are, for example, and being able to consider indicators that are happening at that time and in that particular place. So linking indicators mechanistically to the life cycle and the behavior of different species is going to be really important going forward. So the indicators are less just general information about the ocean and general information about species, and can be honed in more precisely on specific stocks and specific threats that they face. And that brings us away from this part of the IEA framework, which is mainly about just developing indicators and asking what is the status of the system now. More to the risk assessment and the management part of knowing what the pressures are and what do we do about it. Just a couple of examples of that, of relating indicators more to specific risk for specific stocks. Here's a plot that we've developed that shows how California sea lion pup growth at San Miguel Island holds it average to above average conditions when the PDO, that sea surface temperature index, is relatively cool. once the PDO starts to get pretty warm, sea lion pup growth can drop dramatically. So we're identifying thresholds that could be used to inform management. More specific to this group, a recent paper that we published shows that salmon forecast models can also be sensitive to environmental conditions. As sea surface temperature the year before spring Chinook from South Puget Sound were returned, the warmer sea surface temperature gets in that prior spring, the more likely the models are to overpredict the number of fish that come back. So clearly there's a management connection there. So I'll just close with a couple of general thoughts about indicators. I apologize for how rushed this has been. Lengthy and generally consistent time series of indicators, I think, are your friends. They promote these analyses, support these analyses a lot better. Modelers are also your friends for developing models that can produce ecosystem information and also fill in gaps when you aren't able to collect data. It's really important to know what your indicator is indicating and not just assume that it's theoretically the right one to do, and revisit those assumptions from time to time. I think it's very important to have suites of indicators, again, rather than just one indicator that's trying to do too many things by itself. Those suites of indicators can help you interpret the complex ecosystem that we know these salmon are living in. And finally, just to say that we have a pretty full plate in the IEA team, but we are definitely interested in talking more with you about overlapping interests and ways that we might be able to support you with indicator work and analyses. And then Alaska has an IEA team too as well that might also be interested. So I will catch my breath. I really ran through that quickly and I apologize, and happy to take questions.
Great, thanks, Chris. You covered a lot of ground, but that was excellent. You know, I think this is an important opportunity to kind of showcase the full breadth of everything you're up to. It's very impressive. We've got a little over 3 minutes for questions here. I encourage those that are participating to put them in the Q&A box. And while we're waiting for that, I guess just to pick up on your last slide, Chris, I'm curious, you know, thinking about the audience here, right? The PSC family, which spans from the Yukon and Alaska all the way down through the region you've just been talking about. I wonder if you can just briefly touch upon the kind of commonalities or differences between the California Current, US West Coast integrated ecosystem assessments and the Gulf of Alaska / Bering Sea ones. And I'm particularly thinking about whether there's like strong consistency in terms of what you guys are doing, which lends itself even perhaps, you know, better if Canada filled in some of the gaps to tackle things, or if it's still fairly heterogeneous depending on the ecosystem you're looking at.
Well, I think it's somewhat heterogeneous depending on both the ecosystem as well as that customer base, because we do try to define what our projects are going to be. And we try to co-develop them with the people that we hope are you know, going to use the products. And so the Gulf of Alaska group, I think they have a lot of focus on groundfish because that happens to be a pretty hot item for them and their partners. But on the other hand, because a lot of the salmon from the West Coast move up into Gulf of Alaska waters, as Laurie was indicating earlier, it's likely that there is overlap there, and it would just be a matter of talking with them about it. And our collegial relationship with the Gulf of Alaska IEA group is really good. And they're ahead of us on a lot of things, especially, I think, working with small communities and taking into account local and traditional ecological knowledge. So we definitely have a lot of it to exchange and learn from each other.
Thanks, Chris. Got a question here from Kyle Wilson. Are some of these indicators like snowpack flow or nearshore indices available for stocks outside of the California Current ecosystems? And he's in this case thinking of Canadian indicators.
I don't know. We try to focus on the waters that flow into the US managed portions of the California Current in this case, because that's something of our agency obligation. And I honestly don't know how readily available Canadian snowpack and streamflow data are, although there's, you know, I have no reason to believe that it wouldn't be and I've certainly have learned a lot from the some of the DFO workshops and like the State of the Pacific Ocean work or meetings that I've been to. So it's entirely possible. We just don't happen to report it.
Thanks, Chris. I see there's a couple of responses already popping in here with some links to flooding and snowpack data. And I think also saw that Sue was going to put an answer in there. So thanks again, Chris. Really appreciate the presentation. I'm going to take the liberty of switching gears to our final presenter of this first session, excuse me, which would be Dr. Nate Mantua. Hi, Nate. If you can pull up your screen, please. I have the pleasure of introducing you. So Nate leads the salmon ecology team at NOAA's Southwest Fishery Science Center, where he's been since 2012. Prior to joining NOAA, Nate worked at UW as an associate professor, and his research kind of broadly focuses on climate variability and predictability, climate impacts on natural resources, and the incorporation of climate information into natural resource and fisheries management. Back when Nate was a grad student at UW in the late 80s, he was a bouncer at a popular nightclub in Pioneer Square called Doc Maynard's. Fortunately for Pacific salmon and us, today, he wasn't a very effective bouncer apparently, and only lasted the better part of a year. But fast forward to now, Nate, like many of us who've been cooped up at home during COVID, has become one of those pandemic sourdough bakers, and apparently he's gotten really good at it. And his kids are talking about earning some money by selling dad's bread at their local farmers market on Saturdays. So with those fun facts out of the way, I'll turn things over to you, Nate, to wrap up this session by telling us about climate change and Pacific salmon.
All right, thank you, Brendan. And I hope that no one in this meeting got kept out of Doc Maynard's by me. I was, like Brendan said, I was really bad at it, so probably not. So we've already heard from everyone who's talked so far that climate is a really important part of the salmon world. And I'd just like to remind everybody that everywhere salmon live, they are exposed to climate forcing, whether it's in their freshwater, early life stages, or estuarine rearing, near shore, or open ocean. These are all dynamic habitats. They've been affected greatly by habitat that is responding both to the predictable seasonal patterns in the environment, which really gives rise to the seasonal patterns that you see in different salmon life history types and their strategies. But then this more unpredictable interannual variability, decadal variability, or subseasonal variability. And the subject of this talk is how that is likely to change as we get deeper into this century. And before I look forward at what might be coming, I think it's important to look back. And this is also very relevant, I think, to the theme of indicators that we're talking about today, that Beamish and Boyan back in the early 90s started publishing around this idea that the total catch of Pacific salmon and the total production of Pacific salmon had a pattern in it that was related to climate forcing, that they looked at the Aleutian low, this dominant feature in the wintertime. Climate of the North Pacific had a history that had a strong correlation with the history of Pacific salmon catch. And in this case, they looked at the period from 1925 to 1990. And they proposed this idea that there looked to be regimes where in the warmer regimes, say in the early 20th century, and then again, the last 25 years or so of the 20th century, production was especially high. And there was this intervening period from about the mid 40s to 1977, where production was especially low. And in work that I was involved with, primarily with Stephen Hare and Bob Francis, while Stephen was a PhD student in the School of Fisheries at University of Washington, looked more deeply at this issue and Stephen's work was especially focused on Alaska salmon production, which showed widespread increases in multiple species for the 1980s and into the early 90s compared to previous decades. We tried to broaden this up and came up with this idea about the Pacific decadal oscillation, this pattern of El Nino-like climate variability that, at least in what we call the warm phase, where ocean temperatures were warmer than average along the coast of North America and extending all the way into the tropics. At the same time, they were cooler than average across most of the subarctic North Pacific all the way to Asia. And that corresponded with periods of especially intense Aleutian low in the wintertime. And we also looked at the spatial patterns in how this catch variability played out, with these warm periods being especially good for salmon production in the north, but especially poor for a number of stocks on the southern end of the range. In fact, in our first paper on this, we talked about Columbia River spring Chinook, West Coast Coho salmon as tending to have production cycles that were out of phase with those for Alaska pink, chum, and sockeye. And this did sort of give rise to the notion that maybe there are these two regimes following up on the Beamish and Bouillon work, with the warm PDO being especially good for the stocks in the north and the cold PDO regimes being especially good for those in the south and bad for those in the north. And I think looking at the way the science has evolved in the last 25 years now, we see that this is not really a good model for how the North Pacific climate works. And it's also not really a good model for how Pacific salmon production has worked, at least in the last 25 years or so. And I'll note that Beamish and his collaborators had a number of reports that were published in the NPFC that were pushing back on that idea already then, that, you know, it really looks like there are multiple and different kinds of states of climate and salmon production. So maybe this regime concept, it still has legs, but we don't want to oversimplify it and think it just is this sort of two-sided coin. And related to this issue, I think more work that I think has been interesting in helping advance our thinking in the way large-scale climate forcing is influencing North American salmon production is this set of figures from a publication by Kildoff from 6 years ago now. It was in PNAS, where they looked at the smolt to adult return rates for hatchery, coho, and Chinook stocks from Southeast Alaska down into Oregon. And what they found is that there does tend to be coherent SAR variation among stocks for most of the range that they looked at for both coho and Chinook, and that this does have correlation, pretty strong correlation with the PDO index, but it had an even stronger correlation with this other climate pattern. It's been referenced in the first two talks we've heard so far, this North Pacific gyre oscillation. And the North Pacific gyre oscillation is a pattern in the Northeast Pacific that is related to the spin up and spin down of both the Alaska gyre and the subtropical gyre off the West Coast. And when the wind forcing favors an intense spin up of these patterns, it increases the advection of nutrients and of cold water copepods into the inshore regions. And it could be that this is especially good for the early marine survival for a number of these coho and Chinook stocks. And it also has a strong imprint on the sea surface temperature field. And the pictures of sea surface temperature anomaly fields are actually correlations here with the coho salmon pattern of production in the top panel, and then the Chinook pattern, where you have these warm periods associated with low production for most of these stocks. And something that we've seen in the climate literature is that the energy that's being expressed in these different leading modes of North Pacific climate variability, the PDO and the NPGO, has shifted from being mostly or dominated by the PDO to more and more dominated by the North Pacific gyre oscillation. But note that overall, the PDO pattern is still the leading pattern. It's just that its share of the variance has declined in recent years. Something that also changed in the North Pacific climate is that the PDO and NPGO patterns were basically uncorrelated until about the 1990s. And since the 1990s, they've actually had a pretty strong negative correlation with each other, so that there been more in this kind of covariation among the two rather than totally uncorrelated. And something that has also been noted in some recent publications is that there's non-stationarity in some of the biological to climate relationships. And this has been notable, especially for Alaska climate and salmon production. Mike Litzow and collaborators have published a series of papers on this issue. Here's a pair of figures from their 2018 publication, showing that before the 88-89 change in North Pacific climate that kind of gave rise to this increased NPGO expression, you saw that there was a pretty strong correlation between winter sea surface temperature and this principal component representing pink sockeye and chum production in the Gulf of Alaska. In the years since then, up to I think 2015 in the work that they published, that correlation has gone away. That salmon production in most of the 90s and 2000s in the Gulf of Alaska remained mostly high, regardless of where the winter SST in the Gulf of Alaska was. So that is another pretty interesting result, that if you were to hang your hat on the PDO or on this NPGO as a predictor based on some past performance, it may not provide you with a great deal of predictive ability or explanatory power. And something that has gotten a lot of attention, and Gary showed a few of these maps, and so did Chris, that marine heat waves have been a new feature of Northeast Pacific climate that has been a really dominant feature in recent years. And the period from 2014 to 2016, for instance, was record warm throughout most of the Northeast Pacific, including the California current system. 2019, that summer and fall, had another extraordinarily warm period, and that sort of followed on the heels of a remarkable drought and heat waves in Alaska. And then again in the summer and fall of 2020, we had a reemergence of exceptionally warm ocean temperatures in much of the Gulf of Alaska. And if you see, everybody on this call is probably intimately familiar with this as well, that there has just been a lot of fishery problems associated with recent climate extremes. And one of the sort of timelines that I like to keep tabs on that at least provides one way of gauging the socioeconomic fallout of these impacts is the US Federal Fishery Disaster List. And something that I think is clearly happening is that people are getting more and more tuned into the fact that there is a program where they can seek relief, and people are getting better at that. But there's also just this increasing frequency of widespread climate-driven fishery disasters. And many of those are related to California drought, a few Washington flooding, but one of the most frequent things that you see are coastwide warm and poor ocean conditions, leading to low abundance and poor economic returns on fisheries. And I think Gary did a really nice job talking about the broader context of what's going on with West Coast salmon. And this extends beyond the US-Canada border into British Columbia as well, and even into Alaska in some cases, that we've got, yes, a warming climate. We've entered an era of frequent drought and increased frequency of extreme events, including those out in the ocean. And this is impacting an already evolving salmon production system, especially at the southern end of their range, the loss and degradation of freshwater and estuarine habitats, the increasing dominance of hatchery contributions, and then changes in hatchery practices that have really started to hone in on things like releasing really large smolts at a really narrow window of time in the spring. And we see this especially, I think, in Chinook salmon hatcheries, both in California and in the Salish Sea, where this has also been associated with increased synchrony among populations between years, so that the system is becoming more volatile and less reliable. And out in the ocean, there's a lot of changes going on as well, with increases in top predators, including whales, sea lions, harbor seals, and some seabirds, boom and bust cycles and key forage fish populations. It's been really interesting here in California, where the California sardine made an impressive comeback in the 80s and 90s into the early 2000s. And then about 2009, their abundances plummeted. And in 2015 and 16, we saw this development of really large population of northern anchovies in Central and Southern California. And at least in the 2019 surveys, the last coastwide survey showed that there was the highest abundances in the survey history. And then back in the salmon world, at higher latitudes, we're in an era of super abundant pink salmon, at least in some recent years. And Brendan has a really nice paper that looked at the interaction among climate, pink salmon, and the impacts on sockeye salmon production from Western Alaska down into British Columbia and Washington, showing that having this combination of very abundant pinks and warm ocean temperatures has been especially bad for the productivity of southern sockeye. So when we look to the future, I think we're all familiar with the projections. They're pointing towards a warmer, wetter future for most salmon watersheds, especially as you get into British Columbia, Alaska, the high latitudes of Asia, that the projections are that most of the warming, or the greatest amount of warming, will be at higher latitudes. The greatest increases in precipitation will also be at higher latitudes and in the wetter places. So on the windward sides of high terrain that already get lots of precipitation. And it's going to have huge impacts on snowpack and the timing of river runoff, that in places that in recent climate have had sort of marginal temperatures for carrying a snowpack into the spring and early summer, you're going to see a big loss of snowpack, and it will start at the warmest locations, which will be closest to the ocean or in the lower elevations, and it will creep upward. And the very high elevations are likely to see really large increases in snowpack in places like many places in British Columbia and Alaska. And you get into a place like Washington or Oregon, and the Cascade Mountains, the Olympic Mountains actually are very temperature sensitive with their snowpack. So there'll likely be major losses in the spring snowpack and springtime, early summer runoff that comes with snowmelt. And for the oceans, in addition to a warming ocean, we also have these other important changes: acidification and deoxygenation. And acidification is predicted to be especially strong in the subarctic waters of the North Pacific, where salmon live. And same is true with deoxygenation. And this time series on the right side of this graph show that the pace of change in terms of pH, this is from a time series from a model prediction off the Oregon coast, shows that we're just sort of getting into this acceleration phase right now. And it's going to get worse fast in coming decades. And the same is essentially true for deoxygenation, although maybe that's going to happen a little bit later than the pH declines. And something that I think is really interesting too and important is this issue of shrinking habitat, thermal habitat for some of these high seas foraging species like pink, sockeye, chum, and steelhead especially, that we know are the most surface-oriented species. And Steve Lindley and I and some others here have been updating work that was first done by David Welch and collaborators, and then Omar Aziz, a postdoc that worked with me about 10 years ago, looking at the thermal habitat distributions. And these are highly simplified by selecting an isotherm where high seas salmon surveys from the 50s and really the latter half of the 20th century showed most of the fish were encountered. But if the 12-degree isotherm is a good indicator for summer distribution of sockeye, these recent marine heat wave periods took out about 10 to 20% of the area that is thermally suitable. And this doesn't consider food production at all, but I think there are lots of indicators that the recent marine heat waves also came with incredible food stress in many of these regions. And note that the areas in the Bering Sea remained in kind of a good place for sockeye, below 12 degrees, but close to that upper end. And if food production was good, then you have really great conditions for growing fish. But that's not true in the Gulf of Alaska, where the background temperatures are warmer and they're closer to these thermal limits. And other species tend to have a little bit warmer boundary. But projections looking out towards the end of this century suggest that things are likely to get a lot more squeezed in the future, that at least in the work we did, about a 38% decline in winter habitat availability and 45% in summer for sockeye, if that 12-degree sea isotherm is a good metric. And there have been a few climate change vulnerability assessments recently published. There was one focused on the ESA listed stocks along the West Coast and Western states that was published, led by Lisa Crozier. And in this case, we're adding climate stress to already stressed ESA listed salmon and steelhead populations. And of course, it makes things worse. And the scenarios that we were asked to consider were warmer, bigger floods, lower summer low flows, less snowpack, ocean warming and acidification. And this ended up having widespread impacts, especially on the more inland populations that had a life history that exposed them to the river in the summer. So things like stream type Chinook, Coho salmon, and sockeye were especially vulnerable. And pink salmon and chum were less vulnerable because of their more coastal and sort of low elevation distribution and their limited freshwater life history. And this slide, I think I'll just buzz through it because kind of running out of time here, but again, different life history patterns are going to expose different populations to different stressors, and that freshwater rearing that is an extended period for different species and different stocks of those species really adds to the exposure that they're going to realize from climate change. And I thought I would just mention this most recently published paper on this issue. Again, Lisa Crozier, lead author, looking at 8 different salmon river Chinook salmon populations. And they looked at the whole life cycle and did the best job they could do considering covariation among environmental drivers and different habitats, and to follow these populations in an age structured model. And they found that the rising SST in the Northeast Pacific was the most important environmental driver in their future projections. And in part, this is a result of focusing on populations that are in the highest elevation, highest quality spawning and rearing habitat in the Columbia Basin, probably. They're up there in relatively pristine freshwater habitats in Idaho. And it really ended up highlighting the fact that in this case, limiting factors that can be either in freshwater or the marine system have to be addressed if these populations are going to persist in a warming ocean. And just to quickly summarize, we're entering an era with very rapid ocean changes. High frequency of warm events in recent years caused widespread impacts on marine life and fisheries, and that these trends are predicted to continue, and our ability to forecast them in advance is not there yet. Even on this sort of interannual variation, we're not able to do that with high skill. And I also think that in the next decade or two, the slower trends in the ocean are going to be overwhelmed by the short-term variations, and that we're going to continue to see large year-to-year changes. Some of them might be good. In fact, in California this year, we're enjoying one of those periods of colder temperatures, strong upwelling winds, although we're not enjoying all of that because it came with atmospheric high pressure that has diverted the storm track out of California. So we have terrible water conditions in our watersheds. And, we're headed, I think, to a no analog future, that we're going into ecosystem states without historical analogs, and we should prepare for impacts the best we can. And that is going to pose some really serious fishery management and ecosystem management challenges. So I'll stop with that. I see I've taken pretty much all my time, so sorry about that.
Thanks, Nate. That was an excellent talk. Really appreciate it. And a great summary at the end there to leave us with some food for thought while we take a break. We won't have any time for questions at this point, but a reminder for everyone, there will be a panel discussion after our next session where we'll be able to hear more from many of the speakers. So with that, we're sitting at 2:30 Pacific time, and everybody can take a break to stretch their legs, grab a cup of coffee or a glass of water, hit the bathroom, and we'll see you back here at 2:40 sharp for a presentation from Andrea Reid.
I hope you had a nice stretch, and we'll continue on with our afternoon session. And thank you also to all the speakers from the first session, super informative. And remember, you can post all questions in the Q&A or chat box, they'll be monitored. So next up, we have Andrea Reid. So Andrea Reid is a citizen of the Nisga'a Nation and a new assistant professor with the University of British Columbia's Institute for the Oceans and Fisheries. So Andrea, if you can see if you can share your slide, that would be great. And Andrea is helping to launch and lead the Center for Indigenous Fisheries. So she's working to build a national and international hub for the study and protection of culturally significant fish and fisheries. Andrea, we're lucky to have her for her PhD. She received a Governor General's Gold Medal and Carleton University's Medal for Outstanding Doctoral Work. So fun fact about Andrea is that at home, she has a kind of a unique pets, 3 guinea pigs and 2 crested geckos, and they were once thought to be extinct. So with that, I will hand it over to Andrea Reid.
Thanks so much for the welcome and for having me here today. Yeah, so great to be here. Neat. Willa Willina. Hello, how are all of you? As Marisa introduced, I'm Andrea. I'm a daughter, a sister to 3 brothers, and an auntie to 9 beautiful nieces and nephews. I'm a citizen and member of the sovereign Nisga'a Nation, which you see here, which sits on the colonial border created between British Columbia and Alaska. There are indeed Nisga'a who reside on either side of it, and my Gigi, or grandmother, and her mother spent much of their lives moving back and forth across this invisible line that lies in these waters just before the mountain range that you see in the background. We're a matrilineal society, and my Gigi belonged to the Giscast or killer whale clan, and through generations, I'm following her line. Giscast represents breath or life as symbolized by the blowhole and sound of the killer whale. And the gifts linked with the Giscast are the breathing in or giving life to knowledge. And I see these both as my gifts and my responsibilities in my work as a fisheries scientist. I'm a new assistant professor of indigenous fisheries at UBC in the Institute for the Oceans and Fisheries, as well as the principal investigator for our new Center for Indigenous Fisheries that's really dedicated to community-driven science for fish, people, and place. And I'm joining you now from the historical and contemporary territories of the Musqueam, the Squamish, and the Tsleil-Waututh peoples here in present-day Vancouver, which I've recently moved to just last December after having completed my PhD situated in Ottawa, co-supervised by Dr. Stephen Cook at Carleton University and Scott Hinch here at UBC, in which I was focused on the migration biology of Pacific salmon, as well as salmon-based knowledge systems. And I want to be clear here now that what I'm here to share reflects my own views, knowledge, and questions, which aren't necessarily shared by those at my university, nor am I here to speak for all or any Indigenous nation, including my own. So it's my honor to be here today to present to the Pacific Salmon Commission, and I'm going to be sharing a talk I recently delivered as the 2021 Insight Lecture to Fisheries and Oceans Canada. So apologies if this is a repetition for any listeners, but what I was asked to speak to in this context dovetailed really nicely with what I was invited to speak to there, which really centers on the sympatric coexistence of Indigenous and Western science in modern fisheries. So that's what I'm going to run with. So given the history of Indigenous fisheries criminalization, appropriation, dispossession, and dishonoring that continues to this day, we're faced with deep chasms of mistrust and serious barriers to true collaboration that inhibit areas of possible synergy that could contribute to more positive processes and outcomes. And while I'm talking about horrific occurrences of the past and of the present, I'm purposefully showing images here of Indigenous resistance and strength, rather than potentially re-traumatizing those involved in these events with images of violence or hate. What I'm here to share today is not a panacea. The only possible solution or remedy in these contexts are perhaps land back and reinstating Indigenous sovereignty over Indigenous lands and waters. So instead, what I'm offering you today is an invitation to interrogate your own positionality and purpose in your fisheries research and management, and to identify pathways for us all to build towards consensus, where we can come to learn from one another and embrace multiple ways of knowing in our work as scientists, managers, and decision makers. The scale and scope of current ecological and fisheries crises demand that we do things differently today. The dominant paradigm that has relegated fish to resources that can be manipulated for strictly economic gain, which is the very definition of a natural resource, is clearly not working. And we've managed fisheries through this commodified rather than relational lens as a result. Fish are far more than just food, and they're critically linked to identity, culture, ceremony, practice, law, language, and story. They underpin coupled social ecological systems that for much of the history of contemporary fisheries management, we have managed with predominantly ecological metrics, tools, and policies alone. It shouldn't feel revolutionary to say that fish and people are inextricably linked, that fisheries management is a deeply social and ecological enterprise, or that we could do things better if we were to welcome fisheries knowledge, insights, and practices from all of those who coexist in the landscape in which a fishery is set. Co-management offers us one way of working together, but how is it departing from the status quo or doing things any differently if co-management regimes continue to ascribe to strictly Western scientific approaches and ask Indigenous partners to leave their worldviews and bodies of knowledge, belief, and practice at the door if they want a seat at the decision-making table? We have limited financial resources to attend to current ecological and fisheries crises, as well as limited time. So we very much need to confront these challenges, to learn from the best of our collective abilities and understandings, and to do so now, especially given the reality that we inhabit these shared landscapes, and that what we do up or downstream from one another has impacts on the fish who move rather seamlessly between the territories of the people or guardians, as well as the habitats on which they depend. Before I transition into speaking on how we can make space for multiple ways of knowing and equitable coexistence in our shared landscapes, I want to take a moment to acknowledge that throughout this lecture, I'll continue to speak about fish as subjects and not objects. And this is a practice that I've cultivated on my own, principally as I wrote my PhD thesis. I simply couldn't refer to a Pacific salmon as an it and not a who, but I've since come to find that this practice ascribes to a broader movement, what Robin Wall Kimmerer refers to as a grammar of animacy, and has roots ranging from Shakespeare's Julius Caesar to Herman Melville's Moby Dick to Dr. Jane Goodall's In the Shadow of Man. But it, of course, stems far further back and has been a practice carried by Indigenous peoples from around the world, many of whom ascribe to a worldview of living relationship with these other beings on the planet we share, and who see all life as equal, interconnected, and interdependent. I also want to emphasize that Indigenous peoples are not one homogenous group. And while I'm advocating here for the creation of space in our research and management for Indigenous knowledge systems, I want to be clear that these knowledge systems vary by context, geography, and peoples, hence why I talk about them in the plural form. So now back to this question of learning from multiple ways of knowing. How can we create the needed space, or as some of my Indigenous colleagues put it, how can we infiltrate and fundamentally change this system that has excluded and overlooked us and our ways of knowing? We must start by thinking broadly about what science is. It's a systematic way of gathering and condensing knowledge into testable laws and principles. And Western science is one form of scientific knowledge that has roots in the philosophies of ancient Greece and the Renaissance, favoring reductionism and physical law. But it is not the only form of scientific knowledge. Indigenous science is broadly defined as the scientific knowledge of people who, as participants in culture, are affected by the worldview and interests of their home communities. While Western science has aspired to be unbiased, value-free, and objective, it has ignored the very real social context of science that shapes what we ask and why, what we accept as evidence and why, who we deem experts and why, what methods we use and why. The list goes on and on. Indigenous science instead places focus on who we are as individuals in relation to the knowledge being systematically gathered, condensed, tested, and carried forward as principles. And from Indigenous knowledge systems come a variety of epistemological approaches that inherently embrace what is called knowledge pluralism, or the coexistence of multiple ways of knowing. And epistemological might be a kind of scary social sciencey sounding word to some of you listening, but it essentially just means relating to the theory of knowledge, especially with regards to its methods, validity, and scope, and the distinction between justified belief and opinion. Few Indigenous scholars or scholars that ascribe to other than Western ways of knowing have the privilege of not needing to use words like epistemology, because we're so often asked to justify the methods, validity, and scope of what and how we know. We all dream of a future where we can come to a meeting like this and simply share knowledge of fish, where the validity of how we've come to know isn't called into question. The primary mode of academic and management treatment of Indigenous knowledge has often focused on the content and not the epistemologies of Indigenous knowledge systems. In other words, how the academy or management structure can benefit from Indigenous knowledge as data to be fed or assimilated into Western scientific models or frameworks, rather than how we can all learn from multiple ways of knowing in equitable parallel. Indigenous knowledge systems are inherently tied to the knowledge holders and to the landscape in which they're situated. They cannot be divorced from the people or from the land. Indigenous nations around the world have grappled with this idea of epistemic pluralism for a very long time, because there's been a broad understanding of the benefits to be derived from embracing all of the best tools and understandings available to us. Atawaptamuk, or two-eyed seeing, comes to us from Mi'kma'ki, and it centers on learning to see from one eye with the strengths of Indigenous knowledge and ways of knowing, and from the other eye with the strengths of Western knowledge and ways of knowing, and learning to use both these eyes together for the benefit of all. The Guswenta, or Two-Row Wampum, is the 17th century treaty belt between the Haudenosaunee and Dutch settlers, and it was made to symbolize two rows of boats shown by these purple beads, the canoes of the Haudenosaunee and the ships of the Dutch, both in this shared river of existence, symbolized by the white beads, where both sets of boats remain separate, neither disrupting the integrity of the other. Instead, the boats work together on shared problems when needed. In Northeast Arnhem Land, the Yolngu people have the Ganma concept, where fresh and salt water meet in a lagoon or estuary, but remain separate like isohalenes. And the Maori have the Wakaturua, or double canoe concept, that works in nearly precisely the same way, with this working together when needed, but still remaining whole and separate in the process. And there are further metaphorical concepts that bring in a third dimension, for instance, braiding sweetgrass, where two strands representing distinct knowledge systems are held together by a third strand made to represent working together in a good way. And this has been made well known by Robin Wall Kimmerer's book by the same name. in which she also discusses the three sisters concept: corn, beans, and squash. Where corn should be grown first, it's the elder and provides scaffolding for the other plants akin to indigenous knowledge systems. And beans come next. They're curious and fast-growing plants that risk expanding everywhere and taking over if not guided and well-supported by corn, representing Western science in this framing. And then these are followed by squash that creates a microclimate for all the plants by creating shade, making favorable conditions for all to live in balance and to thrive, with squash said to represent the knowledge of plants or the earth, enabling indigenous knowledge and Western science to work together in a good way. And the list surely goes on, but the point is clear that many indigenous cultures have developed pathways to guide how they can embrace multiple ways of knowing without having to shrink or translate or modify their knowledge system so it can fit within Western scientific confines. It fundamentally and quite clearly doesn't matter what you call it. What matters is what you do with it. How can one use any of these as a guide to enable learning from two or more ways of knowing in parallel? This would not only be an avenue towards consensus, but it would importantly also uphold Indigenous rights enshrined in the United Nations Declaration on the Rights of Indigenous Peoples, of which Canada is a signatory, particularly Article 31, which states that Indigenous peoples have the right to maintain, control, protect, and develop their cultural heritage, traditional knowledge, traditional cultural expressions, as well as the manifestations of their sciences, technologies, and cultures, including human and genetic resources, seeds, medicines, knowledge of the properties of fauna and flora, oral traditions, literatures, designs, sports and traditional games, visual and performing arts. They also have the right to maintain, control, protect, and develop their intellectual property over such cultural heritage, traditional knowledge, and traditional cultural expressions. And second, that in conjunction with Indigenous peoples, states shall take effective measures to recognize and protect the exercise of these rights. So the use of really any of these conceptual frameworks that I just introduced, they could be a pathway for states to recognize and protect these rights, but also a pathway for Indigenous nations to exercise them. And there are some wonderful examples of Etoweptimuk and these related concepts being operationalized, many of which my colleagues and I highlight in our recent open access paper on two-eyed seeing published in Fish and Fisheries, as well as in this curated list of essential reads available online through the Great Lakes newsletter. But what they make clear is how context dependent each scenario is. There are generalities that can be informative, such as establishing projects from a place of mutual research interest, identifying together the tools needed to tackle a problem, co-developing and co-evaluating the research itself, sharing recognition and benefits, and positioning these relationships for continuation in the long term. But the precise nuts and bolts of how the co-learning can take place varies in important ways by context. So we can't lay out a clear, prescriptive play-by-play that's going to fit each situation. However, there are things that we can do to prepare ourselves to be ready for this kind of work. And for this, I want to turn to Kwam Huyam, Dr. Joanne Archibald's notion of Indigenous story work, which she defines as the study of traditional practices of storytelling and adaptation of these practices to current day learning. Dr. Archibald provides instructions on how one can get what she calls story ready. And I think much of this holds true to prepare oneself to engage in this type of pluralistic work. The first step that she outlines for us is understanding colonial impact. What are the impacts that colonialism and Western science have had on Indigenous knowledge systems and ways of being broadly, but also specifically in the context of one Indigenous fishery? In other words, what is the history of colonization and what are its results? It's truly everyone's responsibility to know this history and to understand what it means for people today. What is the complex history that culminated in last year's major conflict in Southwest Nova Scotia around the Mi'kmaq lobster fishery? What led to the fish wars of the 60s and 70s here in the Pacific Northwest? What were its outcomes and what do they mean for people here today? Knowing this history, especially in the context in which you work, is a crucial first step. Next, she identifies appreciating Indigenous knowledge systems, Do you treat indigenous knowledge systems as equally valid in your science and management as its own knowledge system with its own scientific and logical validity? Do you even consider how indigenous knowledge systems might come to bear on the research questions you're trying to answer? If not, why is that? These aren't necessarily questions with clear-cut answers, but they are entry points for us to think for ourselves how ready we are to engage with multiple ways of knowing. The third thing she identifies is valuing relationships, seeing good relationships as foundational to our ability to do good work, bringing in the principles of relationality and relational accountability, defined for us by Cree scholar Sean Wilson in his book, Research is Ceremony, in which he posits that ideas develop through relations that we have with others, and that in our research, we're accountable to those with whom we have relationships. And this is a concept that extends well beyond human relationships to really include all our relations. If fish are animate, living beings that we're beginning to think about as relatives instead of resources, what does this mean for how we do our research? What methods are appropriate and so forth? And then fourth and last, she indicates learning the core of knowledge, starting from the inside and then expanding outward. What's the core teaching or lesson or finding? And then considering more broadly how it can be applied. And I recently had the pleasure of hearing Dr. Archibald speak and storytell, and I feel compelled to share one story with you now because I find it deeply pertinent to the work that lies ahead of us. And I recognize it might be unusual to storytell in a context like this, but especially given how zoomed out we all are, I hope that you can take the last few minutes of my talk to sit back, enjoy this, and let your imaginations be free to think about and to feel this story. So this is a story called Mr. Magpie and Mr. Crow, originally told by Stalo Chief Harry Edwards from the Chiam community, and now the subject of this children's book used in local elementary schools. And it goes like this. So one day, Mr. Magpie told his wife and his family that he was going to go out hunting for deer because their meat supply was getting low. And so he took out his bow and arrow and he went out into the forest. And as Mr. Magpie was by a small hill, it was in a bit of a clearing, he was standing there and he saw something coming towards him, just rolling down that hill quite fast. And then it was flat where he was standing. And when he looked down, he saw that there was a deer there, and that the deer had been shot by another hunter with a bow and arrow. So Mr. Magpie thought, well, it's somebody else's deer. So he very carefully removed the arrows because he didn't want to wreck them. And, he wanted to be respectful to the hunter who had caught the deer. And so when he took out the arrows very carefully, he just waited. And a while later, the hunter comes by, and he thanks Mr. Magpie for being really careful with his arrows. And he says, you can have this deer, you can take it home, he said. But what you're going to find is this. When you start out carrying the deer, it's going to be quite light and it will be easy for you to travel to your home. But when you get closer and closer to your home, that deer is going to get heavier and heavier. And so Mr. Magpie thanks the hunter for his generosity, and away he goes. And sure enough, his load is really light. So, he makes good time getting to his house. But when he gets closer, the load gets heavier and heavier. And he just barely makes it to his house, but he calls his family out and tells them the story, and they start to cut up the deer and they give some to members of the community, and they have a nice feast. And then while this is happening, his neighbor, Mr. Crow, was watching, and he was kind of jealous that Mr. Magpie had, gotten this deer and that everybody seemed to be really happy with Mr. Magpie. And so the next day, Mr. Crow decided it was his turn to go out hunting for deer. So he got together all of his gear and away he went. And he went to the same area that Mr. Magpie had been the day before, by a little hill. And he also saw something come tumbling down the hill really quickly, and it landed in front of him. And when he looked down, he saw it was a deer that had some arrows in it. Well, Mr. Crow was kind of angry because, why did somebody else get this deer before me, was his thinking. And he's not happy. So he pulls out the arrows and he pulls them out kind of roughly, and he breaks one of them in the process. And he's still kind of angry. And as he looks down and he's looking at these broken arrows, the hunter arrives, and the hunter says, you can take this deer home if you want to, he said. But what's going to happen is that when you start out, your load is going to be really, really heavy, he said. But as you keep going closer to your home, the load is going to get lighter and lighter. And so that's exactly what happens. Mr. Crow is starting off, and the deer is really, really heavy and he can hardly manage. But as he keeps going and he gets closer to home, the load is really, really light. And he throws it down on the ground. And as he goes into the house, he tells his family he's got a deer out there. He tells them to go out and cut it up. And they go outside and they call out Mr. Crow and say, there's no deer here on the ground. And when Mr. Crow looks down, all that he sees is a pile of bark from a tree. So that's the story of Mr. Magpie and Mr. Crow. And in a lot of Indigenous storytelling, stories don't necessarily have these nice and tidy endings, and they can often end really abruptly in this way. But they also carry a range of meanings. This story could be about respect, treating the hunter, the arrows, the community respectfully, and then being rewarded in a way that seems applicable to the different behaviors of Mr. Magpie and Mr. Crow. But we can also think in metaphor, and we can think about the deer as our treatment of Indigenous knowledge systems and all the work that really lies ahead of us. If we don't value them, or if we think that the hard work is done by simply sitting in on a lecture like this, then the results are surely going to be ephemeral. But if we treat Indigenous knowledge systems with the respect as the valuable entities that they are, and we recognize the path forward will be an increasingly difficult one as we journey down this learning path, and we still choose to go down it, then the results will surely be far more sustaining. So with that abrupt ending, I'd like to say Tuyuk, thank you for your time and attention today.
Thank you, Andrea, so much. You're a very powerful voice, and I'm sure we're going to hear a lot more from you in issues related to the Pacific Salmon Treaty. So we have no time for questions, but I encourage anyone who'd like a follow-up with Andrea to please enter your questions in the Q&A or the chat box. And thank you so much for being with us. So with that, I'm going to transition to our next speaker. So Brian, if you'd like to get your slides ready. Dr. Brian Burke has worked in fisheries since 1993 and joined the NOAA Northwest Fisheries Science Center in early 2002. His interests are primarily in ecological modeling, so everything from small-scale processes such as energetics and physiology of individuals to larger processes such as animal movement, habitat quality, and population fluctuations. Now, a fun fact about Brian is that he wished that he'd learned how to play the guitar when he was a teenager, because learning at this point seems impossible. But fortunately, he's stuck with ecological modeling, and his information in the NOAA stoplight chart is broadly used across the Pacific Northwest to forecast salmon. So with that, Brian, please take it away.
Great, thanks, Marisa. So, excuse me. Yeah, I'm gonna basically give an example of our group's work on how we use indicators and how we select indicators. And to a large extent, I'm going to be talking about some pitfalls to avoid. So if you all are getting into this business of using indicators to manage salmon, hopefully you can learn from a lot of our mistakes. Acknowledge my co-authors, Jennifer Fisher, Sam Zayman, Kim Jacobson, and Cheryl Morgan. The group of us have been working on these stoplight indicators for some time now. And I also want to acknowledge NOAA Fisheries and Bonneville Power Administration and Oregon State University provide funding for most of this work. So if you haven't heard of the or seen the NOAA stoplight chart, this is what we're talking about. It's a pretty basic concept. So along the left here are different indicators of some condition in the ocean. So it could be a local physical thing, it could be a large scale thing, it could be a biological metric, but they're just different indicators of ocean conditions. And then across the top are different years. And so within each indicator, we just color code those cells to represent good, fair, or poor conditions as they pertain to salmon. The benefit of this stoplight chart is primarily a qualitative tool. It's a visual tool. So you can see, I know that the years here are a little bit difficult to see, but 2014, 15, 16, if you scan down these across all these indicators, we see a lot of reds and yellows. That was the blob years. We know those were poor ocean conditions for juvenile salmon to enter the ocean. But we can look at, some of these other years, 2008 in particular, there's a lot of green across all of these indicators. And that was a fantastic year for fish entering the ocean. So that's basically how this table works. And I have a couple of questions I just want to bring to light on this, because they're things I've been thinking about for a long time dealing with this. The first is, are these the best set of indicators for a given application? We put these together thinking sort of in a general way about ocean conditions. This is a good year or a bad year, but the more that we use this and the more that others use this, we've realized that, every stock of fish out there is interacting with the ocean in different ways. They're going in different places. They're experiencing different things. And so, applying this table universally to all salmon stocks is not a good approach. And the second question is, what level of cross-correlation exists within the table? If you've dealt with indicator data or ocean data at all, you know that pretty much everything in the ocean is correlated to some extent with everything else. And so, if we include a bunch of indicators that are very similar to each other, highly correlated with each other, and then one of the things we do here is at the bottom, we just look at the mean rank of these different years. So if we're going to collapse this down to one or two variables that represent all of this information, there is the potential that we bias our own evaluation if we sort of have a bunch of highly correlated variables in this table. So assembling this table is sort of an artwork. And so that's some of what I want to talk about today. In an ideal situation, the variables that are included in a chart like this are all informative. You certainly don't want things like Laurie mentioned, the temperature in Paris, France. You want things that are important or highly correlated with salmon in some way. And I'll go into this later, but you want things that are correlated in a predictive sense. And so I'll talk about that. It's an important point later in the talk. And then again, ideally, we would have correlation among these variables minimized so that when we summarize the data, we know that summary metric is representing all of the indicators, if not equally, at least robustly. We don't want it to just look like the two or three things in the table that are highly correlated with each other. And then, so this is sort of where we are. We've recognized that, applying this one table to all stocks is not a good idea. It doesn't work very well. So we have created what we're calling stock-specific stoplight chart. But the idea here is that and this is all for the Columbia River stocks. But for spring Chinook, as Laurie mentioned, they come out of the river and they go north really rapidly. So the indicators that are important that are related to salmon spring Chinook survival are different than the indicators that are related to fall Chinook survival. And so having these separate tables just sort of solidifies that concept. So I'm going to go through a series of issues that we have run into. And if you're doing a similar, whether you're creating tables or just running models, you're going to run into these issues. So I just want to highlight some of them. The first one is a little bit odd to say, but the fact is there are too many indicators. We have a lot of sources of data and a lot of information. It might not be the best information, but there are a lot of data sets out there. And this list on the right here is just a handful that I came up with just thinking off the top of my head. But the chart on the left is a correlation matrix. So I've hidden the names, but there's basically 30 or 40 variables here that I happen to use in an analysis. And the color here represents the correlation among those variables. So as you can see, there's a lot of deeper reds and deeper blues. Those are high correlations, either negative or positive correlations. And so, as I mentioned earlier, the data that come out of evaluations of various aspects of the ocean ecosystem are all highly correlated with each other. And so that's a problem when we're trying to come up with explanations for why things are happening or make predictions about what's going to happen. Having highly correlated variables makes it very difficult to select among them. Another general practice is to try and be as mechanistic as possible. Some variables are more mechanistically related to salmon survival than others. Unfortunately, they're not often available. So this, I'm not going to go through this sort of complicated looking flow chart very much, but it's something I put together a few years ago, mainly just to help myself think through these complex relationships. But I'm going to make a couple of points here. The primary goal here is we want to understand or model or forecast cohort survival. So that's down here in the bottom right. And to do that best, ideally, we would be coming up with some indicators of things that in this chart are not very far from cohort survival, so that there's very few connections to cohort survival. Those would be the most mechanistic relationships that we could hope for. Unfortunately, what we tend to have in our data sets tend to be more physical variables, large scale things, small scale things, but they tend to be either physical or lower trophic level biological data. And the fact is these are necessarily going to be correlates with cohort survival rather than mechanistic drivers of cohort survival. And just as a quick example, so as I think Laurie mentioned, or maybe Nate, we in the Columbia River Basin, we tend to use cobepod biomass quite a bit. It's one of the data sets that we have a long time series of, and it is highly correlated with a lot of the dynamics in the nearshore ecosystem. But when we think about mechanistically, well, what is the relationship between cobepod biomass or species composition and salmon survival? There's actually a couple different pathways that we could look at. So cobepod biomass could be feeding the adult forage fish community, which can act as alternative prey to a lot of these salmon predators. So that's one important pathway that could be the reason that cobepod biomass is correlated with survival. An alternative is that the copepods are feeding juvenile forage fish species or flatfish or crabs or any other type of salmon prey. And the increased prey or alternative, the increased salmon prey are feeding salmon growth and increasing salmon size and condition, which then feeds into size-dependent predation of salmon. So these things aren't mutually exclusive, but they're also not always in concert. Sometimes one will have a negative impact on salmon survival and one will have positive impact. So again, the point here is that if we could measure these things that are more closely, more mechanistically related to salmon survival, those are the indicators that are going to do the best. The further we get away from that, the more we're relying on correlations that have multiple intermediate steps. Excuse me. Three other things I want to just mention that as you develop data and models, just some things to be aware of. One is that there are cross correlations across habitats in environmental data. So this is a paper that Jennifer Goslin just published earlier this year in Ecological Indicators. And the idea here is that all of the drivers of the ecosystem, but primarily the physical system, are large atmospheric drivers, and they influence things like sea surface temperature and coastal upwelling. But the fact is, they also influence things like snowpack and river flow and river temperature. So, there are, in the Columbia Basin, for example, there are groups of people who will model salmon survival and say, look, river temperature or river flow, this is really important. It's correlated with salmon survival. And other people, including myself, admittedly, will say, oh, no, look, it's upwelling and it's sea surface temperature. And it's really difficult to separate the actual mechanism driving survival because of these cross-habitat correlations. But it is important to try. It's just very difficult. The second issue I wanted to bring up was a related one, and this is what we call carryover effects. And this is also a paper by Jennifer Goslin that's in press now in Ecosphere. The idea here is, Jennifer and her team on this paper modeled juvenile downstream survival, ocean survival, and adult upstream survival. And normally when we model, I'll talk about ocean survival as an example. Normally, if we're going to model ocean survival, we would use things in the ocean as covariates to survival. So the MPGO that Nate mentioned earlier, and sea surface temperature in the eastern North Pacific, those are logical covariates to look at. But what Jennifer did is also included all of these blue variables are things that occurred in freshwater before fish got to the ocean. And she included them as covariates to ocean survival. So the impacts or the experiences that the fish had in freshwater carry over to the marine environment and can impact survival there. So things like river temperature were important in ocean survival. Fish size at outmigration, which was an impact of its experiences in the river, was a significant covariate of ocean survival. So just a tip, don't just look at things that are right where fish are now. Think about where they've been as well. Last one, Nate mentioned this one as well, non-stationarity. This is an example from Michael Malick, published this year in Fisheries Oceanography. And the idea here is, when we model salmon survival with environmental indicators, we're making an assumption that those relationships are static. And what we're seeing repeatedly, time after time in the last few years, is that they are not static. And with climate change, it's going to be even more dynamic. So just as an example, this NPGO here on the top row, these are all for sockeye salmon. And so these plots are correlation between MPGO and sockeye salmon survival on the West Coast. And in the 50s and 60s, you can see there was a negative correlation between the MPGO and survival. In the last decade or two, there's been a positive relationship between MPGO and West Coast sockeye salmon survival. And in the Bering Sea, we saw the exact opposite. So these relationships don't stay the same, and we need to not assume that they do, and in fact test and verify how these relationships are changing over time. I was told not to put any modeling details in here, so this is my nuts and bolts slide. Reminder to myself to stay away from the details. I tend to be a modeler, so I need that reminder. So instead, I will just give an example of an application that we have in the Columbia River Basin. So this is going to be an example of spring Chinook at Bonneville Dam. So this is the first dam that they encounter as adults coming back into the river. And what I'm showing here is just the abundance of spring Chinook adult counts over the past decade or so. You can see it's highly variable. The phenology changes as well. Sometimes in this pink and gray, they come in early, sometimes they come in late. So phenology is definitely a component of this that's important. But the variation in the numbers of adults is quite high. And before I go into the example itself, this is as close to nuts and bolts as I will get, I promise. But this is a really important distinction because I'm going to talk about a couple of plots in the next slide. Normally, if you're a modeler or talk to modelers, you've heard about AIC, and the basic premise here is, so we have some data here in the circles. These lines are a bunch of competing models, and we say, well, which one's best? I said earlier, we got all these potential indicators we can use. How do we filter through them? So modelers tend to use AIC as a measure of fit to the data. So the lower the AIC, the better the fit, and that's how you select your indicators. Unfortunately, fitting the existing data isn't always necessarily the best thing. For our purposes, we also want to be able to predict next year or the year after. And so an alternative way to think about selecting variables is using something like one step ahead predictions. And so these are 10 different variables. It looks like the fits are the fit is much worse than using AIC. But what I'm using here to select models is the mean absolute error. And the idea is, so let's say we fit the data through 2009, and we ask, well, how good is it at predicting 2010, given that it hasn't seen 2010? It doesn't know what the answer is. How good is the data at predicting next year? And so it's an alternative way to sort through the models. And one I suggest you highly think about, especially if you're just getting started. Just don't even worry about AIC. Think about model prediction and predictive ability. Sorry, a little tangent on nuts and bolts. The reason I did it is because I'm going to show a couple of slides here, and I just wanted you to understand that these are all forecasts. Each one of these lines is the one step ahead predictions. And so this example, this table is the spring Chinook stoplight chart that we have for the Columbia River Basin. We condense that, so there's 10 variables in here. Each one is represented by one line. And the prediction for this year is in here in one diamond. And then I summarize that table and into a summary metric, and that is this larger diamond here. So the forecast for this year was 48,000 adult Chinook coming back to Bonneville Dam. And we still have, I don't know, 2.5 weeks left of the season. And right now, I think that the adult count is at about 37,000. So the final count might be a little bit above 48, but it's certainly not going to be above 76, which, you know, if you look at these prediction intervals, they're pretty small compared to the variability we've seen over the past 20 years. So these models are doing really well. And then we could do the same thing for fall Chinook and Coho. For Coho, we're using a measure of survival rather than adult counts, but the methods are all the same. And you know, those models included jack counts, so that the sibling regression that Laurie brought up earlier in her talk is part of this model. But the fact is, because Chinook in particular go out into the ocean and spend more than 1 year there, knowing the conditions that they entered when they entered the ocean is important and can be enough to forecast without jacks even 2 or 3 years into the future. So not all managers are going to need that information or be able to use it, but if knowing 2 years ahead is important or useful, we can do that with ocean indicators. Final thing I want to mention, I'll go through this quick. I don't want to run out of time here, but I can't remember. I think it was Chris mentioned, you know, embrace modelers, embrace new techniques and quantitative tools. They can bring to light things that are not immediately obvious. And I'll give a quick example. So this is a sibling regression. So it's in log space, but the number of jacks in year T is correlated with the number of adults in year T plus 1. This is the basis of all sibling regressions, this correlation. And it looks pretty good. And so that's why we continue to use them. However, if we color code these points according to what year they are, and specifically whether they're 2006 or later, you can see that this relationship has changed. So this is one of those non-stationarities that we've talked about. And it's super important, because if we didn't know about this, we would draw a single line through this set of points. And for any given number of jacks, we'd say, okay, well, that line is, you know, going to tell us how many adults there are. But if we know that the relationship has shifted, and we're, you know, in recent period, we're going to look at this orange set of points. We're going to estimate a different number of adults, and this has actually been a problem in the Columbia River in the last few years. We've been overestimating adults because we haven't accounted for this shift. And a lot of these new methods. I'm not going to talk about dynamic linear models, I promise, but if you're interested, I can do this in the future. And the fact is, these new techniques can not only account for these shifting dynamics, but take advantage of them and make next year's prediction better than it would have been had we not accounted for it. Okay, just some quick conclusions. Bee stock specific. These fish are all doing something different in the ocean, going different places at different times. It matters. Mechanistic indicators are best, but they're often expensive to collect or are just difficult to obtain. So sometimes we just have to deal with the more correlative indicators. It's important when you're assembling your set of indicators to think about performance, but also information redundancy. You can overwhelm or bias your answer if a lot of your indicators are just sort of replicates of each other. So you want to reduce information redundancy across your indicators. And then finally, embrace these new tools and technologies. If it means hiring a modeler, it's well worth it. It's money well spent. There's a lot of new things coming out that are just really amazing at teasing patterns out of data. Okay, thank you. And I may have 1 minute for questions.
Thank you so much, Brian. So we do have a question from Chris Kern at WDFW. So Chris asks, are the stock-specific stoplight charts and data available online as the aggregate is? Same site?
Yeah, not yet. There's a couple of tweaks we're still doing with it, and so our goal is to get it up there within a month or something. Yeah, we're sort of finalizing things now. So check back often or email me. Yeah, I'd be glad to let you know when we have them.
Great. Well, so Brian, also if there's more questions for you, we'll provide them and you can have a written response that we'll post on the PSC website link to this workshop. But thank you so much, and we will be moving on. So our next speaker is going to be Sue Grant. So Sue, if you can get your slides ready. Sue, along with Bronwyn McDonald, leads DFO's State of the Salmon program in Fisheries and Oceans Canada. So the goal of the State of the Salmon program is to track and understand Pacific salmon trends. And recently, climate change and climate variability has been identified by Sue and her team as being a really important driver of recent salmon productivity and declines. So with that in mind, Sue has been a very generous human thermal probe of climate change throughout the world. And so fun fact about Sue is that she likes to get into hot water. And she'll elaborate a little bit about this, but she's traveled the world and has bathed in many hot springs the world over. So to learn a little bit more about that and the state of the Fraser River sockeye, I'll turn it over to Sue.
Thanks, Marisa. Myself, so I guess the lead in is I like to get into hot water in my personal life when it comes to hot springs, but that kind of sentiment stops at what I'm about to talk about. This is when this level of heat is not the same. I lead the State of the Salmon program along with Bronwyn and McDonald, and we've been leading this program for 3 years. And prior to that, we were leading DFO's sockeye analytical program. And one of our key roles in that program was to make predictions, forecast returns for Fraser River sockeye populations in the upcoming return year. One of the fundamental things that we bring to all our work, Bronwyn and I, is integration. So really pulling in experts from a range of disciplines, freshwater marine ecosystems, working on the animals in different locations, and creating integration, pulling that science together. So a lot of what we're going to be talking about is those integration processes that we've developed and lessons learned. Today's presentation is on our experiences forecasting for Fraser River sockeye, including work we've been doing in more recent years. And it's titled Chasing Predictions in a Rapidly Changing Climate. So it's really about our lessons learned. And a lot of people have contributed to this work over the years. So there's a lot of co-authors and other people feeding into this. With all this integration work, climate change, human-induced global climate change has emerged as a driver. It's embedded within all the other factors contributing to ecosystem and salmon trends that we're currently seeing. We've had some good introductions to this already today. Temperatures on the planet are warming, and in recent years, we're hitting record warm temperatures. It's not just about climate, temperature, and Nate Mantua talked about this. We're also seeing more extremes in precipitation. We're seeing periods of drought. And so it's a bunch of things mixed up into that. And at our local scales that are relevant to our salmon, Pacific salmon, this global climate change driver is embedded. It's interlinked with all these other factors, and you can't really separate them. Climate change is influencing the increased frequency of forest fires we're seeing. It's directly increasing river temperatures, ocean temperatures. It's impacting more shifts in species distributions, invasive species, food webs, and I could go on and on. And it also interacts with habitat changes that we're causing, human alteration, but also the forest fires, the pine beetles, and all of that. So that's a long way of saying it's really intermeshed with everything. You can't separate it. We've been, I think in the last decade or so, I think we're kind of hoping that, we see some bad years in our salmon or bad years in our ecosystems. And we're always hoping, well, it's just a blip. It will go away. And we're kind of like a frog in a boiling pot of water where we're not radically changing our approaches to the changes that are occurring. This warm blob is something that kind of, I think, jolted us out of this thinking, because this is a pretty dramatic change, this marine heat wave. And when it started in 2013 and it persisted all the way to 2021, it didn't go away. It changed a little bit, moved around a little bit, but it stuck with us. Marine heat waves, the science links these to global climate change. And in a way, they are jolting us out of this hot water that we're in, and hopefully making us look around and think differently about how we're thinking about current and future, the ways we're doing our science and our management. These heat waves are predicted to increase under global climate change. So they're not going to go away. We're going to see them increasing in frequency, intensity, and the spatial area that they're covering in the ocean. Our catch is responding, our salmon are responding to these changes, these broad overarching drivers and a lot of other drivers that are embedded within this global climate change driver. This is a figure of catch, includes all kinds of catch within our Canadian fisheries over time for our 5 key species that Fisheries and Oceans manages. In the first 70 years, our catch was 24 million. And then in the last 35 years, it dropped to under half of that at 11 million. And then during these heat waves, we had a further reduction, dropping down to 4 million in the last 6 years, and then 2.5 in the last 2 years. So I think the combination of these profound events that we're seeing in the ocean, and then our salmon systems, and we've got our management systems turning the cranks annually, and we're seeing these pretty profound responses in our salmon as well. And so it's all kind of jolting us out of this things will get back to normal, right? Kind of perspective. I'm going to walk through forecasting. So the journey of forecasting, finding environmental indicators, and some lessons learned along the way. And it really, I think the preceding presentations really, there's a common theme moving through them and a lot of connections. So I think you'll see some common themes emerge. When I started forecasting in 2007 for Fraser River sockeye, we were largely just turning the crank. We had a lot of other jobs to do, and it was really just running an analytical process. using retrospective analysis like Brian Burke described to pick top models, and then generating forecasts. We included environmental variables at the time, largely ocean variables with a bit of Fraser discharge during smolt outmigration. At the time when I started forecasting in Fraser River sockeye, we weren't really tracking productivity and talking about it much. And I think, again, this gets into the frog in a boiling pot of water. We're not really paying attention. We kind of are, I think, optimistic, thinking this trend is just part of a downturn blip and that we were going to get back to normal at some point. So we weren't paying too much attention to it. At the time, forecasts were associated with high uncertainty. Going into 2008, we started to really value expert judgment, pulling in our expertise to think about the forecast more. We emphasized marine environmental conditions, and we're starting to look at what do the current environmental indicators in the marine environment, how do they match to what we've seen in the past, and how do those past observations relate to productivity? So what can they tell us about current productivity? So we really started to think a lot more. We weren't turning the crank. We were thinking about the models we were using and we were pulling in expert opinion. The models and forecasts were still associated with high uncertainty, but we were moving more towards this expert judgment approach and pulling in expertise, mostly among the world of people who really understood Fraser River sockeye population dynamics on a high level. And that included Mike Lapointe at the time, and Kathryn Michaelsons and others started to get involved. In 2009, we were really impressed with the NOAA approach that Brian Burke just described. At the time, it was Bill Peterson who was working on these. And we started to formalize the indicators we were using in the marine ecosystem. So we were using variables, matching it to what we thought were relevant to Fraser sockeye in the Strait of Georgia, as well as variables that we had access to, like boreal shelf copepods on the west coast of Vancouver Island, not totally related to the Strait of Georgia, but we thought they would be reasonable indicators. In 2007, like when we look back when we started to develop these, we're like, well, it did work pretty well in 2007. We didn't use it at the time, but it was the lowest productivity on record and all the indicators were bad. 2008 was indicating slightly better productivity and the Fraser sockeye aggregate improved. So we were seeing some good things there. Then for 2007, ocean entry year, which is the 2009 return year, we said, oh, things are looking okay with our indicators. We were also warning that we hadn't done all the work to validate and cross-check all of this. So we weren't hanging our hat completely on this, but it was adding to the quantitative forecast process. We didn't get any warning signs from freshwater marine scientists before the season started. So there was nothing to tell us that anything was going to be bad. We had no warning signs. And of course, everyone knows what happened. The Fraser sockeye return came in extremely low at 1.6 million, and it was the lowest productivity on record. So the indicators kind of disconnected here for us. We've learned some things along the way, and that's kind of what I'm going to talk about in terms of using indicators. It might be possible that these indicators were relevant in certain years and they become less relevant in other years because different drivers are playing a role. And it's not necessarily everything is turned on and off in one year. It could be that one bottleneck is driving everything in a particular year. So it's a cautionary tale about using those in certain contexts. So when we went into 2010, we started the laborious Cohen inquiry, a legal inquiry into the declines. Everyone started to realize that we were in this sort of lower production period. And as we were going into this, we started to add new models. We're like, well, we're in a different phase of productivity. We're adding new models that explicitly accounted for lower productivity. And we were kind of using current conditions to tell us something about the future year's productivity. Again, we had no advanced warning from any marine or freshwater experts to warn us of anything good or bad. And what happened was the complete opposite of 2009. We were blown away by an unexpected record high return of 28 million. So this experience and then being in the middle of an inquiry as well really hit home. We've got to figure out another approach to get people working together and breaking down silos and really looking at Fraser sockeye population dynamics in quite a bit more detail. So we started up an integration process where we pulled together our freshwater marine experts across the different life cycles of Fraser River sockeye. And largely, a lot of these scientists and stock assessment experts, we work in isolation. We're running a million miles an hour, doing our own programs, but we hadn't been working together, breaking down silos. So we started to do that, sit in a room for several days and talk to one another and ask and interrogate one another in terms of what we're seeing and putting that story together. So looking at the conditions during adult upstream migration, the water is getting increasingly above 18 to 20 degrees Celsius, which is extremely stressful for fish. Looking at the research that links stressful conditions to legacy effects on the quality of offspring, monitoring of the health of the parents and the juveniles. We had lake research programs, Dan Selby's program, talking about how certain lakes like Cultus Lake are dramatically responding to climate change and the synergies of that with nutrient eutrophication, and other systems like Chilko Lake that are doing a lot better under climate change. We were looking at the Mission Downstream program that Joe Tatey runs and others, looking at the quality of the fish, migration timing. We're looking at Chris Neville's program, the quality of fish health in the Strait of Georgia. And then Mark Trudell and now Jackie King's program we were looking at in coastal waters around BC. We lose track of the fish as they migrate north and into the Northeast Pacific. Well, we do track them along the coast, but once they get into the North Pacific, we don't have a lot of information other than the environmental indices and indicators out in the ocean. So there's a couple of years where we're just tracking broad scale trends. I want to emphasize that when we're doing this, we're looking at individual stocks, and there's considerable variation in terms of the rearing locations, the upstream migration timing, and the conditions they're facing. There's variability in downstream migration timing, physiology, even amongst the fish, and it's teasing out that kind of detail. So we provide this every year, work together. We've slowly turned this into a more rigorous process, and it's these kind of expert-driven processes that are, I think, really helpful to breaking down silos and also looking at cumulative effects and looking at how in some years there can be a bottleneck in a freshwater system, like a landslide or a huge flood that's a scouring event for a certain system. That's the bottleneck. That's what's going to cause the problem for some populations. In other years, it can be cumulative, poor conditions throughout the life stages. And other years, it can be a bottleneck in the Strait of Georgia. I think part of that is why we had challenges with the stoplight approach. So every year we go through this, we pull out key observations, and then we describe whether the effect is positive, negative, or neutral, how confident we are in that effect. So for example, upstream migration temperatures above 19 degrees Celsius, we know is a negative effect, and there's a lot of research to link that. So we called it very likely. And then we talk about the effect on the overall Fraser sockeye survival. And we do that for the adult migration stage, the egg stage, any monitoring we have of the health of the adults and the fish eggs stages, the juvenile rearing in the lakes, smolt downstream migration conditions, and then the ocean. And then we work together 3 days, pulling this all together, and then we come up with an overall recommendation. And in recent years, we're generally putting it all together and indicating negative survival effects and a likely confidence associated with that. We do this, as I said, on individual levels as well. So looking for bottlenecks within particular populations and trying to tease apart sort of nuances. And we tried to convert this, Bronwyn did a lot of work trying to convert this into something that's prettier, like a stoplight approach. And we're just finding there's just too much detail and too much nuance to be able to convert it into anything that's just a stoplight approach in this case. Our work in recent years by integrating across staff has predicted lower survival. So that's the advice we're providing, along with the quantitative forecasts, which remain uncertain. And it provides additional information to just say, with all of the information we have, we're not seeing any indication of really good survival. So not expecting this sort of bump up. I think the important thing to emphasize with all the work we're doing is it is an ongoing learning process, and it's all about breaking silos and not sitting by yourself and doing, like when we started, we were forecasting more on our own, but we gradually built into really bringing in broader and broader groups of people. And I think there's a long way to go to continue to reach out, because solving what Gary mentioned at the start, solving wicked problems in a very complex problem space is going to take lots of different thinking, and bringing in a wide variety of expertise. And we've just sort of begun that, but I think there's a long way to go in breaking down silos. I think Nate's talk really emphasized that there's going to be a lot of surprises. When we're looking at the past to predict the future, things are changing, and we're seeing environmental conditions that are falling outside of our historical range. And we don't really know how systems are going to respond. And we also don't have all the information. So when we're going through our integration process with all of the experts that we bring together, we also recognize and get frustrated at times because there's so much that we don't know at the individual population level. Like, why is one population doing better? What information do we need to tease that out? Why are some populations doing better than others? Why are some doing particularly poorly? We have some information to fill in the gaps, and in other cases, we still have considerable knowledge gaps when we're trying to put that together. Climate change is going to continue, and even under the best case scenario, and this is from the Pacific Climate Impacts Consortium from University of Victoria, our warm years of today are going to soon be average to cool years of the future, even under the best case emission scenario, if we really kick back our greenhouse gas emissions. We're on track currently under a high emission scenario. And that means the warm years of today, the anomalies, the warm blobs are going to be the cool blobs of the future. So I think this is just a warning shot. We were involved in a fishery, food and agricultural organization of the United Nations meeting a few years ago with countries from around the world looking at adaptive management of fisheries in response to climate change. And we really focused on Fraser River sockeye, and some of the take-home messages from that, and sort of to tie up the talk. And I think it links into what a lot of other people have been saying today. We're seeing environmental conditions we've previously not observed, and more extremes and more uncertainty. So we really need to consider more precautionary management approaches and recognize we really, really don't know what we don't know. There's gaps in our knowledge, and being precautionary is a wise move. We also suggest that we should be using environmental and biological indicators across all life stages, and looking at where in some years bottlenecks can be in freshwater, other years it can be in marine, sometimes it's cumulative, but there's a lot of integration work that is required that we need to be thinking about, pulling everything together through structured processes. And I've just described one that we've used, but there's others as well. Our wild salmon numbers are declining, and we're seeing an increasing number that are facing a risk of extinction. And that means we've got to start looking forward, not just a year ahead to providing a forecast for the upcoming salmon season, but a forecast for the next 10, 15, 30 years. And we need to look at crozier approaches that were mentioned in previous talks, thinking about what salmon are more resilient, what are more vulnerable to climate change, looking at different management strategy approaches under different projections of climate change, so that we can start aligning our management systems now to this new future. So this is not just fisheries, but habitat and hatcheries are becoming increasingly important as a management system. And we need this more forward-looking approach rather than just thinking about 1 year ahead. Before we get all that science mobilized, we have to start breaking down the complexity in some of our management systems. and be more adaptive and flexible. The more rigid and the more complex the system is, and there's work on this just even for human societies, the more complex we are, the more likely we are to break under extreme environmental change. And so it's sort of behooves us right now to start looking at our fisheries management and other management systems and breaking down that complexity and looking for that adaptation and flexibility. So I kind of am ending this indicator talk on a really big note that there's ways forward integrating, and I think integration should not just extend to thinking about next year, but it should start getting us thinking about the next few years. Where should we restore habitat? Where do we think salmon are most resilient? And how do we start aligning now to that future, because we're already seeing it, and the future is going to look very different under climate change. And that's my closing point. Thank you.
Thank you, Sue. So that last slide is a good segue into a question that we have from Kurt Hughes. So Kurt is asking, from one of your early slides in your talk, how much the change in catch of Fraser sockeye over time was due to management changes versus environmental change. So response to things like SARA listings, the PST.
Well, I mean, just so I totally understand, catch is responding to two things, I guess. It's being reduced to compensate for the number of fish we need on spawning grounds to ensure sustainability. So it gets dialed back because overall numbers are dropping. And it's also being reduced to account for weak stocks, some of our stocks that have been designated endangered or at risk. So in that mixed stock fisheries context, you'll get dialing back of fisheries in that way too, but it's responding to those two things. And I'm sure a manager could provide a more in-depth response, but ultimately it's responding to declines in productivity overall and also stocks of concern.
Thank you, Sue. Well, that's all the time we have. So we'll move on to our last speaker in this session before the panel discussion. So Kathryn can, as she's getting her slides prepared, I'll provide a brief introduction. So Kathryn Sobocinski is an assistant professor in the Department of Environmental Sciences and the Marine and Coastal Science program at Western Washington University. So she's an applied marine ecologist focusing on fishes, fish habitats, and impacts of human disturbance and climate change in coastal systems. And we're lucky to have her because she's been chasing spawning herring throughout Puget Sound the last several weeks. So some interesting things about Kathryn. She does not just preach ecology, she practices it. So once while sailing off of the coast of Panama, she bought some lobsters from a local fisherman, only to feel very bad at how undersized they were, and then proceeded to repatriate them back to the nearest patch of reef. So she's also a fan of the Sicilian tradition of gelato in brioche for breakfast. So an ice cream sandwich for breakfast. So girl after my own heart. So with that, I will turn it over to Kathryn to talk about a more hypothesis-driven approach to using environmental indicators in a system we haven't talked that much about today, Puget Sound.
All right, thank you, Marisa, and thank you all for inviting me here. I'm coming to you from what is now Bellingham, Washington, on the ancestral homelands of the Lummi and Nooksack peoples. And a small caveat, often the joy of going last is that you get to weave together aspects of everyone else's presentation into your presentation. Unfortunately, I had to teach in the middle of this meeting, so I missed a number of the presentations in the middle. So if I say things that don't seem connected, it's not that I wasn't paying attention, I actually wasn't here. So sorry to those of you in the middle. I wish I could have been here more. I'm now at Western Washington University. Most of the work I'm going to talk about today, or all the work I'm going to talk about today, I completed as part of my postdoc, the Northwest Fisheries Science Center with Long Live the Kings, as part of the Salish Sea Marine Survival Project. So this work has been published in 2 papers. Most recently, This hypothesis-driven statistical approach for identifying ecosystem indicators for Coho and Chinook salmon was published in Ecological Indicators earlier this year. And then we also have a steelhead trout paper that came out in Progress in Oceanography last year. And as has been noted several times, at least that I caught, steelhead are a little bit different in terms of their life history. And so they were treated somewhat differently, although that paper was foundational to the Coho and Chinook paper. And please, if you are unable to get these due to a paywall, please just email me. I'm happy to send you a copy. So do not pay. This work was really based upon 3 previous papers that documented these declines of marine survival, specifically in the Salish Sea. So 3 papers, one for Coho, one for Chinook, and one for steelhead, about these declines over time. And if we look at these time series for the Salish Sea, various Salish Sea basins, for Chinook, Coho, and steelhead, the take home here is that there are overall downward trends. This is logit, smolt to adult return to marine survival, logged or plotted against the ocean entry year. And we see these sort of overall declines, but there's a lot of variability as well. And so the goal of this project was to understand what factors within the Salish sea stocks really influence this reduced marine survival relative to coastal stocks from this same region, and in these 3 species that we focused on. So this was sort of a Salish Sea oriented project. Most of what I'm presenting today is from Puget Sound because the data mostly came from Washington Department of Fish and Wildlife. So for Coho and Chinook, we focused there, just given some project constraints and ability to get comparable data across the border, which is not actually an insignificant problem. So I've heard a couple of people mention salmon as ecosystem integrators. So we know that they have this sort of complex life history where they're moving from freshwater out into saltwater at different stages, returning at different ages, having all sorts of different approaches to attacking this problem of anadromy. But if we think about it sort of on a landscape scale or a seascape scale, as I like to think about it, we really need to start integrating all of the different aspects. And when I took on this project, I think I started in 2015 or 2016, there had been much work done out in the ocean, and there had been much work done in the freshwater, but not as much work done in the inland seas of Puget Sound and the Strait of Georgia. So I think that has definitely changed in the last 5 to 6 years. There's more emphasis on these inland waters now as this project and various others have gotten up and going, and Sue's program and Jennifer Bolt and Jackie King, various other folks. So it's nice to see this ecosystem being considered as part of the seascape that the salmon are migrating through. But it also makes it really complex. The Salish Sea is a highly urbanized ecosystem, and there are lots of different factors that could be at play in terms of reduction of marine survival during this phase. So the project, the Salish Sea Marine Survival Project, had some articulated hypotheses sort of surrounding it at the beginning. And these fell into 3 major categories. So bottom up, top down, and anthropogenic or cumulative impacts were sort of in the bottom, the 3rd one. When I took this on, the question was, what are the factors responsible for the reduced survival of salmon in the Salish Sea relative to the coastal stocks, or specifically this marine survival question? And I came from sort of a food web background, and so I was really excited to dive into the food web and come up with some awesome conclusion about that. And then as I got into it, I realized there's actually not a ton of data for that part of the ecosystem. And so we started brainstorming what other potential indicators may be interesting to this question. And we started with things like boundary conditions. So this is both freshwater and ocean, also atmosphere climate interaction. So your large scale climate indicators that many people have referenced today, but also conditions within the Salish Sea. So what is it about this inland water that makes it maybe perilous to salmon, or maybe not? Is it something about stratification or zooplankton availability or forage fish availability, primary production, all these different things that are taking place in this inland waterway? And then the food web component. So predators and competitors. What are the different forage fish abundances? Birds that are preying on out-migrating salmon, fin fishes that might be preying on out-migrating salmon, and pinnipeds and other mammals as well. We also acknowledge some anthropogenic impacts, things like harvest, contaminants, habitat loss, and various other things. And then characteristics of the salmon themselves. So abundance of outmigrants in the system. So this includes hatchery releases. We've lost a lot of wetland habitat in the lower reaches of the rivers and in the deltas and estuaries. What effect was this having? Density dependence that's been documented in some cases, the timing of outmigration, and then the size and growth of these fish. So there's really a brainstorming of all the different potential indicators we could look at. And we started going down, I'm going to mention this just because this whole thing is sort of based, the work on, that I'm ultimately going to get to is based upon some hypotheses. And we use this technique called qualitative network modeling to kind of game out some of the different hypotheses that we might consider in a quantitative setting. So this model uses just defined relationships between the various components. So we have kind of some oceanographic components here, some sort of base of the food web components here, other, sort of food web aspects here, aspects of salmon themselves, residency, survival, abundance, these things, and then anthropogenic impacts that are kind of around the edges. So the point here isn't for you to know what each of these boxes mean, but just to say that this was somewhat foundational to our approach of developing actual sort of mechanistic hypotheses, was trying some of these scenarios in a qualitative setting and trying to see what the outcomes were for these things that we were interested related to salmon survival. The other problem we quickly came up against with indicators, and I think this has been mentioned a number of times, that an indicator is a quantitative measure that helps provide insight into the state of the environment. They should be theoretically sound or have some sort of tie to mechanistic response. You expect them to respond predictably to some sort of ecosystem change. They should be integrative in terms of taking multiple aspects of ecosystem properties, physical, chemical, whatever, and sort of integrating across them, and then relevant to management concerns. So I'm going to add a couple more. One of the things we quickly found was we had a lot of time series that didn't really show any change over time, and these were not that informative to our efforts. So a good indicator is one that is changing over time or has some sort of ups and downs that that the organisms may respond to. And the second one, I think this has been mentioned, is that they have to be available. If we don't really know what was going on, we only have a few current years of data, then our ability to sort of take a time series and apply these indicators is somewhat constrained. And then lastly, we felt as we were moving from the qualitative modeling into quantitative modeling, we felt that it was really important to come up with solid hypotheses. And I'll walk through those in a second, but we wanted this to sort of, as part of the Salish Sea Marine Survival Project, we had sort of these large scale hypotheses of bottom up, top down, and anthropogenic impacts, but we wanted to narrow in a little bit on specific processes that are sort of based in these hypotheses that might be driving variable survival. So just to give you the conceptual framework of how we worked through this, so we started with this qualitative network model, just sort of gaming some things out. We had data from 1970s to present. And we started generating some hypotheses based upon our current understanding. So we know that seal abundance has increased as smolt to adult return or marine survival has decreased. We thought that increased herring abundance or prevalence of forage fish in the system coinciding with salmon outmigration might lead to increased SAR and various other hypotheses. So we started to build these. And then ultimately we wanted to produce a statistical model that could take these predictor variables and model marine survival. So that's sort of the lay of the land for where I'm going next. One of the things that many people have touched on today, I think starting with Laurie's talk, is that the relevant scales for potential indicators have to include sort of this local scale. So we're talking about in Puget Sound here, this more regional scale that might include things like coastal upwelling, what's going on with the Fraser and sort of dynamics in the straits as the fish are making their way out. And also in the global sense, the North Pacific Ocean, what salmon are experiencing when they're at sea. I mean, they spend most of their life at sea, so we can't, we don't want to diminish the importance of that area, although we also have lesser information about some of the maybe food web aspects or various other things. So thinking about these scales and how they're nested was an important part of setting up these hypotheses. And we at first went down the road of explicit scales and evaluating those. And then we decided that each hypothesis, we wanted to nest the scales together. So the important thing here is to realize that global and regional conditions influence local conditions and vice versa. So estuaries and inland waters like the Salish Sea are influenced by these larger scale processes that are continually changing, not just seasonally, but as we've talked about on a number of cases with climate change and various other marine shifts over time. But it's also important to note that anthropogenic impacts locally can impact fish beyond the inland waters. And this is what Brian Burke referred to with the carryover effects. So there are things like contaminants that the fish show signatures of these while they're well offshore. So not just in the Salish Sea. So there's this sort of back and forth of scales of influence in this area. Okay, so now I'm going to get specifically to this paper and the work that we conducted as part of it. It was actually a very large body of work, and I'm probably not going to do it full justice in this presentation, but especially just because the results are so complex. So I'm going to focus more on the setup and guide you through some of the results. So we ultimately came up with 7 different hypotheses that we wanted to focus on. So we had one related to predator buffering. So this was sort of the abundance of fish in the system mitigating predation. So the hypothesis here was that if there were a lot of forage fishes or a lot of other salmon, that the relative impact on any one stock might be less. We also wanted to think about this in terms of timing. So we know that the hatcheries release their fish at a similar time every year. And we know that estuarine habitat and delta habitat is somewhat limited in many cases. So we're wondering what that pulse of fish coming through at one time, whether that might be drawing in predators as like a subsidy that's coming from out all at once, that there might be a draw for things like seals, or maybe it's buffering the predation from those things by having sort of strength in numbers. So that's the second hypothesis. The third one is the density dependent aspects of food availability and competition. So this is the combination of food availability and other competitors in the system. So if there was a scarcity of prey, that might result in low marine survival. The other side of this is the density independent approach, which is looking at food availability timing. And we don't really have great data in Puget Sound for sort of production of salmon prey. So we used a bunch of proxies here, things like primary production as measured by chlorophyll and various timing of events in the spring. So that was the density independent component. We also had a water quality hypothesis. This was basically conditions within the Salish Sea maybe being unfavorable. So this includes salinity, temperature, and various stratification index and things like that. Hypothesis 6 was water delivery timing. So this was the freshwater impact. And we really wanted to focus not on what was going on the river, but how the freshwater was impacting the estuarine system within the Salish Sea. So this is delivery timing mostly. So when is water arriving? Is it protracted? Do we have a long winter? Did the fish have a lot of time to kind of get used to the osmotic changes from freshwater to saltwater, that kind of thing. And then the last one was anthropogenic impacts. So looking at the impacts of human population, including harvests that might be negatively impacting survival. So we had these 7 hypotheses. For each hypothesis, we came up with indicators that we could get data for under them. And we had anywhere from 5 to 12 indicators within each hypothesis. So here we're looking at something like total small fish abundance as a function, or marine survival as a function of total small fish abundance. And we would hypothesize that as that total small fish abundance increases, marine survival might increase. So this is just one example. From there, we had to generate these time series. I think Chris Harvey gave you a better visual with these than I did here. But we had to check for all these things that people have talked about. So correlations, collinearity with other variables, lags, might the time period of aggregation determine whether that indicator is good or not. So we wanted to get the Salish Sea stuff for when we thought fish were in the Salish Sea, but then get the ocean indicators for when we thought fish were in the ocean. So just figuring out those time periods that where we wanted to aggregate data was an important step in this process. I know I'm not supposed to give any nuts and bolts, but for those that may be interested, we used generalized additive modeling, which is kind of a flexible approach that allows for sort of nonlinear fit. So here's a linear model and here's a GAM fit to the same data. But it has some problems in terms of overfitting and estimation. So we constrain the models a little bit so that to try to eliminate overfitting. And then we used AICC, which I agree with Brian Burke saying that that's probably not the best way to do this, but it's the way we chose for this approach. I think that the one step ahead prediction or leave one out methods are probably better. And then from this, we generated a composite best model with variables appearing most often. So we got the best models for each hypothesis and then a composite model with the variables appearing most often in the most supported models for each hypothesis. So what our output looked like is something like this. This was an unruly table before the wonderful Sue Kim took and made it into nice infographics. So we have the suite of indicators included in each hypothesis here. The direction of the relationship, these are not actual data. These are just sort of cartoon. The variable importance weighting, so how frequently this occurred in the suite of most supported models. And then within the best supported models, these are all, so we have our best model on the top, and then the ones with the delta AICCs are sort of diminished support going down, but these are all still well-supported models. And you can see we've got R-squareds kind of around 35, 36% for in the best case. And these are the factors, the covariates that were included in this suite of best models. So in the paper, there are a number of tables like this for each hypothesis. What I really want to show you is sort of the output in terms of our predictive ability. And if you look at the graph here, so we've got marine survival index and ocean entry year on the x-axis. The black line is the observed data, the observed time series. This is for Coho of all the stocks that were included. And then you can see there's quite variable performance. Each of these colored lines refers to one of those 7 hypotheses, or the model predictions for one of the 7 hypotheses. So all the best hypotheses were all kind of greater than 30% in their ability to fit the data. And the only one that wasn't was hypothesis 6, was the freshwater discharge. That one was really poorly fitting in all cases. So that's just something to note as we move forward. So another thing, we put together these composite models. So these were all of the indicators that appeared as the best, most frequently occurring indicators in each hypothesis. So then we took them and put them together. And for Coho, we really came up with only two best models that sort of fit the data at the end using this reduced suite of hypotheses. And one was sort of abiotic in nature. So that's the one that includes air temperature, precipitation, stratification, North Pacific index. And the other one was a little bit more biologically driven. So with seal predation and Strait of Georgia herring, we had an index of Strait of Georgia herring that we used as well. And so there were some other factors in these, but what you can see is they're a little bit different. And if you look at certain years, one predicts much better than the other. And I think this is coming out through a lot of the talks that I was able to catch, is that the suite of indicators is really key to coming up with a good predictive model, because in some years, some aspects, one predictor or another will do better than another indicator. And we kind of formalized this in addition to just looking at it and realizing that, geez, these were really having variable performance in some years. Some were really hitting the peaks and others weren't, depending upon the year. We actually did an error assessment, and this was based upon the fact that we kind of observed some breaks in the actual response variable. So in our marine survival index for Coho and Chinook salmon, Coho specifically, it looked like the marine survival index kind of changed over time. So it sort of sloped off with these breakpoints. So we used a breakpoint analysis, which I'm not going to present, but it's in the paper, to come up with some breaks. And these are not that different from what others have come up with. We think that there was probably a regime shift kind of around 1989, 1990, in between there. So that one was pretty hard. And then this most recent period of kind of 2014 to 2015 was also somewhat different, with kind of persistent low survival instead of this downward trend. So what I've got here is each of the hypotheses are shown in some colors here. And then our variable, the two best models that I just showed in the last slide, are the two at the end. So these are all, this is Excel, so it should be easy to see that the variable importance weightings are the ones at the end. And you can see in any period, certain models perform better than others. So this is hypothesis 6. It just was sort of universally always the worst one. But they're the ones with the least error. So you're looking for the low error bars here, kind of varied by time, right? So this hypothesis 5 actually was pretty good in some cases. And these best models tended to be the lowest of all. But just looking across these time periods, this kind of stresses what other people have said about, things are changing and they will continue to change. This project as it stood right now didn't really have a forecasting component that was, that's sort of on the list of to-dos, never really got there before the paper got too unruly to include that. We did do some forecasting with the steelhead trout, so you can check that out in that paper. But it is important to realize that there is this non-stationarity going on, and what variables might be predicting survival in any one year are likely to be different. So coming up with a suite of best predictors or best indicators is really the key. You don't want to put your eggs in one basket. You want to get a suite that performs the best. So we only were able to explain 30 to 40% of the variation in the data set with our best model. So it's okay, but not great. I was a little disappointed. I was hoping it was going to be a little bit better. And our freshwater input indicators typically did the worst. So seal abundance was strongly supported. This correlates with the time series, but also mechanistic work supporting predation hypotheses. Also, the hatchery release timing. So we looked at the coefficient of variation, so how protracted the hatchery release timing was in any given year. And we found that more protracted hatchery release timing favored survival. So that's something that we might want to look at a little bit more thoroughly to try to figure out how release timing might help boost survival in these stocks. And the same, as I said before, the same suite of indicators may not perform well over time. So it's important to come up with a suite. And then forecasting models might be able to take into account newer data streams that we didn't have time series for as part of these data and as part of this project. So some of the challenges are that our indicators were based on hypotheses, but there are limitations to this purely statistical approach. We really would like a better mechanistic tie for some of these things. Some of them were quite proxy in their nature. And then correlated variables might explain the variance, but they may not be the most important factors to consider for the same reason. These mechanisms are not well articulated. So indirect and interaction effects are not captured well at all. That's something an ecosystem model would be better suited for, if not necessarily for prediction, but just to understand those. And then we had some potentially important data streams that just don't exist in Puget Sound. And that's sort of young of the year forage fish, a time series for zooplankton, and various other things. So those were limiting. I'm going to wrap it up here to allow time for one question, but thank you very much. I'd like to thank all the people that provided data, the people that developed the smolt to adult return data sets, and the Salish Sea Marine Survival Project technical team as well. Thank you.
Great, thank you, Kathryn. So like I said, there's no questions on the chat, but if people think of things, please add them. And also a reminder that the link, the workshop link on the PSC website has information on all of the speakers, their biographies, as well as links to some of these publications they've been referencing or websites or important reports. So please check that out. And we do have one quick question, I believe. Do we have a question? Okay, from Greg. He is asking, are hatchery impacts on wild salmon considered in these indicator analyses? For example, releasing billions of pink salmon each year into a warm ocean has potentially large impacts on other species like sockeye through competition for food. Are there indicators to account for this in forecasting? If not, it seems like a major gap. So a quick response.
Yeah, great question. So we did use this ocean salmon index based on the work that Greg Ruggiero has done with just looking at total salmon abundance in the ocean. So it's accounted for somewhat indirectly there, but yeah, that's a good point. And I think that there could be a little bit more attention paid to that. Thank you.
Great, Kathryn. And if there's others, we'll post them and we'll follow up with you. But now let's all take a moment to stretch and breathe, and we'll rejoin at 4:30 for the panel discussion with all of our wonderful speakers today.
Well, welcome back, everyone. I hope you have hung in there till the end, and if you have, congratulations. My name is John Holmes, and I'm the Canadian co-chair of the Coho Tech Committee, and I'm speaking to you from the traditional territory of the Snaimo First Nation in Nanaimo, British Columbia. For this panel discussion, I've been partnered with Brian Beckman to moderate this session. Brian's having some bandwidth issues, so he'll be lurking in the background, taking notes, and you're going to mostly have to listen to my voice. Hopefully you won't have to listen to much of my voice, because I'm hoping that we'll have some good conversation with our presenters. Before we go any further, I'd like to thank each of the speakers for generously giving us their time, their expertise, and their knowledge. I thought that all of the presentations that we saw earlier in this workshop were hugely informative and provided a lot of things for all of us to think about. We thought it would be appropriate to finish the day by opening a dialogue on environmental indicators. And so because we only have about 25 minutes for this, we sent each of the speakers the questions that you can see on the screen beforehand, and asked them to prepare some thoughts on any questions that they wish. Brian and I, and given Brian's bandwidth problems, it would be myself, will ask the questions and then invite any of the speakers who wish to respond. So it'll be a bit free form. And we're not trying to be definitive with this conversation. Rather, we're looking for a diversity of views, and we're hoping that you'll begin to think about environmental indicators and how you might use them or not in your role within the Pacific Salmon Commission. You can help the conversation by putting your comments and questions into the question and answer box and upvoting them. If there's enough time at the end, then we'll put the top vote getters in terms of questions or comments to our speakers for a quick response. If there isn't sufficient time, then we'll capture the comments and questions and we'll solicit responses from our speakers. If there's a huge number of questions and comments, then we can't guarantee that everyone will be answered, but we will do our best to get answers to those that are presented to us. And those responses will be included in the workshop documentation that will be forwarded to you later. So with that, on with the conversation. And I'll put the first question out to all of our speakers. What are the characteristics of good environmental indicators to support assessment and management? And I just invite them to rather than raising a hand or something, just start talking.
Yeah, I'll offer one response, and I think that it's important to custom tailor indicators or indicator sets as much as possible to whatever the question is. And if it is specific to a given stock, make it appropriate for that stock, and whether it is abundance or distribution or maturation rates or whatever that question is, you want to do the best job you can in custom tailoring it. And one example that I've been involved in was in translating the results of a retrospective modeling study, similar to things that we heard about here, that looked at the life cycle for fall run Chinook salmon in the Central Valley. And in that work, looking back at what explained the history of escapement over a 30-year period, it identified a few things that really stood out. And they were throughout the whole early life history. So spawning escapement for the parent generation, incubation temperature for the eggs, winter flow related to the rearing and outmigration survival rates, and then an index of seabird diets at the ocean entry point. The Farallon Islands are located just outside the Golden Gate Bridge, where these fish first enter the sea. And then the fishery harvest rate that's applied to the parent generation, to actually the stock that's coming back. So that you can't know in advance. So in terms of understanding the past, you can tie into things like that. And in terms of, characteristics that are important, easily updated and understood, there are mechanisms that link the indicators to this issue, and that it's integrative, that it's not just focused on one piece of this complex life cycle. And that, I think, is something that I've seen just in the science, looking at trying to explain smolt to adult return rates. A lot of that on the West Coast, at least, has been born out of this trend towards hatchery dominated stocks. We've really put the freshwater production system under our control. So we know how many smolts go out every year, and we're feeding them at rates that produce a certain size individual fish. And, and then there's released at a time that's under our control. This example I just gave you was actually applied to a composite stock that's both natural origin and hatchery origin. So those are some of the things that I think are important to consider. And then I think we also heard from a number of speakers that you want to be flexible enough that you can incorporate change, because using this in a forecasting mode, which we're not doing, actually, we're using it more just an indicator, informational mode. There's going to be some surprise. Something different happens, and then all of a sudden your system, if it's a predicting model, it'll fail. And then you want to understand, well, why did that fail? What did we miss? And it's not surprising that things fail, because these are really complex life histories that are exposing fish to this incredible range of different habitats. And the bottlenecks that they face in any given year can be really different. And that is not going to go away. That's going to be part of the world that salmon management, sort of salmon fisheries world, is going to continue to operate in, I think.
Thanks for that. Good advice. Good ideas there. Are there other thoughts?
I would agree. I think Nate summarized things extremely well, and very much agree with what he was saying. And I'll just add to that, when he started out saying, you have to focus your indicators on kind of what's your stock of interest. I would also add to that, and I don't think this is inconsistent with what many others were saying, is what are we trying to do with the indicators now? And a lot of the messaging I have is, we've got to be really, it's kind of a big, I think it's a more provocative kind of comment, but, if we're sort of stuck with our heads down, producing predictions for next year and turning the crank every year on these complex management systems, it's a comment on looking up and saying, well, what are we trying to do? Things are radically changing, and we know unless we rein in greenhouse gas emissions, we're on this pretty big trajectory. And what do we, by integrating our knowledge on the ecosystems and putting it all together, what are we trying to do with that? Because if we just keep our heads down and we're just trying to predict what's happening next year, we're missing the forest through the trees, and we're not looking up and saying, what are the big things that all our science, all this insight that we learned from these presentations today on how things are connected and integrated, and how Nate just said, 1 year, a bottleneck could just be a slump or a landslide in a particular river system, and that's your bottleneck. Another year, it could be a flood. Another year, it could be the marine environment. So how do we take all that and look up at the forest and say, where are we going, and not just get stuck in this sort of annual cycle? And that's a sort of like asking us to look up and reevaluate our questions.
Rather than look in the rearview mirror, look ahead.
Yes.
Thanks. Okay, I'm going to move on to the next question, and that is, how important is it to understand the mechanisms underlying observed relationships between environmental indicators and salmon abundance, survival, whatever your variable is, before using them to inform salmon management? Do we need a mechanistic understanding, or can we just find something that works and come up with the mechanistic understanding later?
I guess I'll take a stab at this. It's really just supporting what Nate and Sue just said, though. You know, in the Columbia Basin, what we've done to a large extent is use correlates of survival in our management. And so things like PBO has been used by countless managers because it's correlated with everything else that happens in the North Pacific. So for years, it did a fine job at sort of estimating how many fish would come back, or what condition they'd be in, or what state the ocean was in. But in more recent years, it's not doing as well. And people are like, what's going on? What happened? This was our predictor. But the fact is, it didn't have a mechanistic, at least a direct tie to survival. And so, Nate's comments and Sue's comments about recognizing, well, what are the drivers of survival? And, I really appreciate Sue's comments about not just thinking about, survival in one place. It can happen, I think it was Laurie talked about some of the work that Dick Beamish has done over the years. And so this one theory was, this critical period, as soon as fish get to the ocean, the first few months, that's the most important part. Another one was, well, that first winter is important. That's when, what sets cohort strength. And the fact is, it bounces around. Some years, it might not be in the ocean at all. Some years it's that first couple of months. I remember in 2015, I think, in the Columbia River, Laurie Weitkamp caught a bunch of fish in the estuary, and we didn't catch any of them in the ocean less than a month later. So, it can be this extremely fine temporal period that drives the cohort, the levels, or it could be something that happens, in December in Alaska. And so if you're going to have indicators, you have to recognize, why is this thing correlated with my stock of interest, and recognize that that's a correlation. It's not always going to hold, and it's going to change over time.
Okay, thank you. Others?
I think one thing that, if I could, sorry, jumped in here, that might be important here to realize too, is that there's a certain amount of exploration that can happen without knowing the mechanisms that might set some research priorities outside of management that may better inform management. So I don't think that we necessarily want to go into the management aspect blind, but some of the exploration of things that we don't quite fully have fleshed out may help. Like I think in Puget Sound and the Salish Sea, the seals one has been a good one because it's popped up a number of times, and now there's a number of mechanistic studies that are starting to give some weight to the fact that seal predation may actually be considerable. And so that's one that I think of from my experience that, we didn't really have it totally fleshed out at the beginning, but in the last 5 or 7 years, there's been a number of additional mechanistic studies that have really provided support for that. So I think Brian said something about, use the modeling tools, or maybe Chris. And I think that there is this feedback that can happen across the various disciplines that will ultimately inform management as you start to point towards where the mechanistic gaps are and take those on.
Yeah, I'll just jump in to say that I really agree with Kathryn's comments. And I don't think we always need that. I think a mechanistic understanding is obviously something wonderful and that we want to work towards in so many contexts. But when we look at the gravity of the situation and the crises that our salmon fisheries are in so many contexts, we really do need to make decisions when information is limited. And I really like Don Hall's question in the Q&A box, talking about a specific indicator on the west coast of Vancouver Island. And I think that there are many times when we might not understand the mechanistic understanding, but we can still, take some knowledge and guidance from what is being provided by it.
Okay, thanks for all the responses. And I'm going to move on to the third and the final question in this sort of mini panel discussion. And that is, what is more informative for salmon assessment and or management? Monitoring ecological indicators such as predators and or prey abundances, or oceanographic indicators such as sea surface temperatures, PDO, and or upwelling? Are we talking about polar opposites here, or are we talking about a mixture?
This is Laurie. I'll jump in, and I think that using biological indicators are nice in the sense that they already integrate their response to physical conditions. So there's already kind of this level of translation that goes on that kind of, even if you don't know where that biological indicator is relative to your species of interest, like Brian Burke showed, I think it's still, they're telling you something by how they're responding to the physical conditions. So you've already kind of eliminated some of those. And I think they're, in that sense, they're informative, although they can also be very unpredictable as well.
Okay, thank you.
I'll follow up with that idea too, that there's a really interesting thing that happened here off the west coast of California in the last 5 years. I mentioned that anchovy abundance has become very high after being very, very low just 6-7 years ago. And the conceptual models or the paradigms for understanding anchovy in the California current prior to this period of abundance was that they did best during cold, strong upwelling, kind of sustained cold PDO periods. And of course, that's not what we've had at all. And they're super abundant now. And they're the dominant forage fish for a number of top predators that range from salmon and halibut up the food chain to many seabirds and marine mammals, even humpback whales. So we wouldn't have gotten that with tracking sea surface temperature or upwelling. We would have nothing there. And as Laurie said, the ecosystem is going to integrate lots of different things that are happening in ways that we don't have the capacity to predict all the time or even to translate. So that's really critical. I think if we could get our hands on a number of ecological indicators at different parts of the food web and understand how they interact, who is eating who and where are the things going on. But even then, here's another wrinkle. These super abundant anchovies that are being fed on by everything look to be contributing to a thiamine deficiency in Chinook salmon in California in the last 2 years, which impacts the reproductive success of the spawners, so that they're fat fish, they're growing great, but their eggs are thiamine deficient. And this nutritional deficit, if it persists, will have a huge negative impact on the productivity and abundance of this stock. And nobody had seen that on the West Coast before. So, again, I'm stuck on this issue of ecological surprises as the ocean changes rapidly and in many ways unpredictably. And I just kind of wonder what's next. What are we going to see that's just so different from what is part of our historical understanding? And it does, force me to think, we have very limited capacity to track everything that's important in real time, and predicting it is especially difficult. And it does point towards a need for more holistic and integrative approaches that are also more fundamentally focused on what makes these populations persist and thrive. And it sort of challenges the kind of Western science reductionist approach to try and sort everything out that we need to know in order to manage in a really mechanistic way. And I think, you know, it's hard not to look at West Coast salmon management and just see this incredible failure in recent decades, that we have crises on top of crises right now. And there are lots of contributing factors, but I think we've heard from a couple of people, we really are at a point where it's time to step back and think about how we can protect these animals and the communities that are connected to them in the face of such incredible environmental change, with climate change and ocean acidification likely to get much, much worse going forward than what we've experienced in the past.
Thanks for that. I agree. Any other comments? Well, not hearing anything. With your permission, I'll move to the Q&A box, and we have a couple of questions in here, so I'll put them to you, recognizing that you're getting them cold. So whether you have a response or not, we shall see. The first one is from Marianne, and she says, I think it's a dance between bottlenecks each year, for example, low flow, high freshwater temperatures versus ocean dead zone during outmigration. Can the modeling incorporate a kind of meta-analysis to try to use environmental indicators to predict which bottleneck is in effect for a particular stock or any brood year? So maybe then you know which environmental model to use that year.
I guess I'll take a stab at that's really hard. I think the closest we could come is either using tools that incorporate all of those things in one analysis, or do some sort of model averaging where, you know, if you have a suite of models and they each give you an estimate for what's going to happen next year, the one that happens to be a bottleneck is going to be an outlier. And so, you know, you could just take the average of all your model predictions, or you could pay a little bit more attention to outliers and say, you know, this has the potential to drive the dynamics for the entire cohort. What's going on here, and, you know, maybe use that to drive an extra investigation or something. But it's a conundrum we deal with all the time, and it's not easy to solve that question.
Okay, thank you, Brian. And very quickly, with 20 seconds left, Peter Katinich asks, how do we consider the evolutionary plasticity of these animals in the context of abiotic and biotic shifts moving forward? How can this influence our forward thinking for forecasting or management? And we're just about out of time.
I'd say that's a perfect topic for a future workshop.
Indeed, and we will endeavor to get some responses and put them into the workshop documentation. And so over to you, I guess, Laurie? Or
actually, I think Brendan.
Brendan, sorry.
I think I'll take things away from here. Thanks, John. So I want to yet again extend a big thank you to all the speakers today for generously sharing your time on yet another video call, as well as all the attendees that participated and tuned in. We had, you know, great participation today. We covered a lot of ground. We've been trying to take lots of notes, you know, from Gary right off the bat, setting the stage with the PST, environmental change, to Laurie talking about the distribution of salmon at sea, Chris introducing us to the integrated ecosystem kind of assessment lens that he and colleagues are taking on the US West Coast, and Nate providing us with a broad scale perspective on Pacific salmon and climate change, and a a no analog future. We then transitioned to Andrea, who talked to us about the importance of engaging with multiple ways of knowing and really challenged us, I think, to reimagine the role of indigenous knowledge in fisheries management. Brian shared a bunch of great lessons learned in the development and application of the NOAA stoplight approach to thinking about salmon survival. And then Sue shared her experience with chasing predictions and Fraser sockeye in a rapidly changing climate. And Kathryn, you rounded things out with a discussion of a hypothesis-driven approach to trying to identify ecosystem indicators that influence Coho and Chinook survival in the Salish Sea. So thank you all. Really appreciate you taking the time to share your perspectives and the great presentations today. As a final reminder for everyone, we will be sending around a post-workshop survey that we'd really appreciate you taking the time to complete. We'll be reporting back out on that and on this workshop and your post-workshop feedback in the not too distant future. So please stay tuned for that. And with that, best wishes all, stay safe and have a good evening.